Hello there, and welcome to Physics with William, where curiosity gets cozy and science takes the scenic route to sleep. Tonight we are settling in with a very small troublemaker, one of the least famous and most important things in the universe, the gluon. It is a particle with a name that sounds almost helpful, almost tidy, almost as though it should sit politely in the corner and hold matter together like a dab of cosmic glue. That, unfortunately, is not its style at all. The gluon does hold things together in a sense. It helps keep quarks bound inside protons and neutrons, which means it plays a direct role in the existence of atoms, stars, planets, cups of tea, sleepy scientists, and whatever surface you are currently resting on. But the moment you try to imagine it as a neat little binding agent, like the universe carrying around a tube of adhesive for emergencies, it wriggles out of the picture and starts behaving in ways that are far stranger, far livelier, and much less cooperative than the name suggests. Before we get into that, I would love to know where you are listening from. Are you tucked into bed in a quiet room, winding down after a long day, or listening under a lamp with the rain outside, or perhaps half pretending to work while secretly thinking about quantum fields? And while we're at it, what time is it where you are? It feels oddly appropriate, does it not, to ask that at the start of a story about something so tiny and yet so foundational, because the universe is full of scales that do not seem to belong together. Your evening routine and the inner life of a proton do not look like they should have much to say to one another, and yet here we are. If you find this soothing, interesting, or simply a pleasant way to let your brain drift through difficult ideas without having to fight them, do consider liking the video and subscribing. It helps this quiet little corner of physics find other people who would also enjoy hearing about the most stubborn particles in nature at an hour when most sensible conversation has already gone to bed. And now let us ease into it gently, because the gluon is one of those topics that can sound simple for about 30 seconds and then become gloriously unreasonable. At first glance, the basic sales pitch seems straightforward enough. Matter is made of atoms. Atoms have nuclei. Nuclei contain protons and neutrons. Protons and neutrons are themselves made of quarks, and quarks are held together by gluons. There, all done. Very tidy, very educational, perhaps even mildly impressive at a dinner party, depending on the dinner party. But that neat summary is a bit like saying a hurricane is just some moving air. Technically not wrong, but leaving out almost everything that makes it a hurricane. The gluon belongs to a family of particles known as force carriers. These are the messengers of the fundamental interactions, the go-betweens that allow particles to affect one another. Light has the photon. The weak interaction has its own heavy carriers. Gravity, if we ever pin it down in the same way, would have a graviton in many theories. And the strong interaction, the one that binds quarks together, has the gluon. So far, so respectable. The trouble begins when we ask what kind of messenger the gluon really is, because most messengers simply carry information or influence from one place to another. They do not then turn around and get tangled in their own message. The gluon does. It is not just delivering the strong force. It is part of the strong force in a very direct and deeply inconvenient way. This is where the story starts to develop that particular look physics gets, when it has stepped beyond ordinary intuition and is now waiting to see whether you will follow. I hope you will, because this part is worth it. To understand why the gluon is so peculiar, it helps to begin with the quarks it interacts with. Quarks are not little marbles sitting still inside a proton like peas in a pod. They are quantum objects, which means the old image of tiny balls bouncing around like ingredients in a soup is only useful up to a point, and then becomes misleading. But even with that caution in place, we can say that quarks are the ingredients out of which protons and neutrons are built. They come in different varieties, and they carry a special kind of charge related to the strong interaction. This charge is called color charge. Now, before your mind starts filling with paint swatches, this has nothing to do with ordinary color. Quarks are not secretly red in the way apples are red. Nor are gluons tiny decorators choosing an interior palette for the proton. Physicists borrowed the word colour because they needed a label for a three-way kind of charge, and for reasons known only to history and perhaps sleep deprivation, they went with red, green, and blue. This is charming in a slightly dangerous way because it sounds more visual than it is. Still, the name stuck, and now generations of students must quietly accept that the universe has a force based on colours that are not colours at all. Quarks carry these colour charges, and gluons are what allow those charges to interact. If that were the whole story, the gluon would already be important. But what makes it truly strange is that unlike the photon, which does not carry electric charge, the gluon itself carries colour information. In other words, the very particle that transmits the strong interaction is also caught up in it. Imagine trying to deliver a letter while also being made of the same argument the letter is about. It is that sort of situation. The messenger cannot remain neutral. The messenger joins the brawl. And that is one of the reasons gluons refuse to behave in the nice simple way we might wish. They do not merely travel between quarks as clean little exchanges. They interact with quarks, yes, but they also interact with one another. They can bunch, split, rearrange, and contribute to the intensely active inner life of a proton in a way that makes the whole picture much more crowded and much more dynamic than the cartoon version many of us first learn. When people first hear that protons are made of 3 quarks, they often imagine a crisp arrangement, perhaps 3 stable components locked in place by a few hard-working gluons doing the fastening. But that is more like a children's book version of events. Inside a proton, things are busy. Very busy. Quarks are present, certainly, but there is also a restless sea of gluons and fleeting quark pairs appearing and disappearing in the quantum churn. The proton is not a quiet container. It is more like a tightly packed storm of activity, with gluons playing a central role in the whole ongoing commotion. This is one of the first big mental shifts that the gluon asks of us. It asks us to stop thinking in terms of static objects and start thinking in terms of fields and interactions. In the world of modern particle physics, a particle is not just a tiny bead. It is also an excitation of a field, a ripple or local disturbance in something more fundamental spread throughout space. So when we talk about a gluon, we're talking about the quantum ripple associated with the strong interaction field. That sounds slightly less friendly than calling it glue, I know. It also happens to be much closer to the truth, and yet even that does not fully capture its personality. Because some particles in physics seem almost polite. They are difficult, yes, but they keep to certain boundaries. The gluon seems to have looked at the boundaries and decided to treat them more like suggestions. This is why it creates one of the most famous and frustrating features of the strong interaction, confinement. Confinement is the reason no one has ever picked up a single quark and displayed it neatly in a jar, which is probably for the best because the jar would need a very impressive label. Quarks do not appear alone in nature under ordinary conditions. Try to pull 2 quarks apart and instead of weakening as distance increases, the strong interaction remains powerful in a way that makes separation increasingly difficult. It is a little like stretching a spring that does not want to let go and grows more insistent as you pull. Put enough energy in, and you do not isolate one quark. You simply create new particles. The system finds another way to remain in company. Gluons are deeply involved in this. Their self-interaction helps make the strong force unlike the more familiar electromagnetic one. With electric charge, the influence weakens with distance in the intuitive way you might expect. With the strong interaction, the behaviour is more complicated and, in some important respects, opposite to that expectation. Quarks can move around each other at very short distances in a way that is strangely loose by comparison. But try to drag them far apart and the whole arrangement resists fiercely. So the gluon is not just binding things, it is enforcing a rule. No lonely quarks, no quiet exits, no slipping out the back door. There is something almost comical about the mismatch between the name and the behaviour. Glue, as we usually imagine it, is passive. Sticky, perhaps annoying, occasionally on your fingers when you didn't ask for it, but fundamentally passive. A gluon is not passive. A gluon is active, self-involved, and central to one of the most dramatic forms of organisation in all of physics. It is less like household glue and more like an overcommitted event coordinator who is also part of the guest list, the seating chart, the kitchen staff, and the argument in the hallway. And this matters because without gluons, the visible universe would look very different indeed. Quarks would not be bound into protons and neutrons in the way they are. Atomic nuclei would not have the same ingredients. Ordinary matter would lose much of its structure. In fact, a large fraction of the mass of familiar matter comes not simply from the bare masses of quarks themselves, but from the energy of their interaction, and gluons are at the heart of that story. That is one of the most remarkable things about the world at this scale. The mass of the stuff around you is not just a matter of adding up tiny constituent bits like weights in a grocery bag. Much of it emerges from motion, confinement, and the energetic bustle of fields interacting. So in a very real sense, the gluon is helping write the heft of the ordinary world. That is a fairly astonishing job description for something so obscure. It sits at the foundation of matter, shapes the interiors of protons and neutrons, and still manages to be absent from most casual conversation. Photons get all the glamour because light is visible and lasers are dramatic. Electrons get a fair bit of attention because electricity has obvious public relations advantages. Gluons, meanwhile, are doing some of the heaviest lifting in existence while sounding like a craft supply. There is also a practical reason they can seem elusive. We do not detect gluons in the simple, clean way one might hope. Because of confinement, they do not usually show up as isolated little visitors. Their presence must often be inferred from the patterns they leave behind in high-energy experiments, from the sprays of particles and the detailed behaviour of collisions. In other words, the gluon is essential, but not eager to pose for a portrait. It is more the sort of particle that leaves the room in disarray and expects you to deduce that it was there. Now by this point you may be wondering what a gluon really is in the most direct possible sense. Is it a thing, a wave, a packet of force, a disturbance in a field, a bookkeeping tool in equations, a real entity? The slightly unsatisfying but honest answer is that in modern physics it is all of those descriptions to varying degrees depending on how you're looking. At the deepest level we currently use, the gluon is the quantum carrier of the strong interaction, the excitation associated with the field governing colour charge. That is the clean answer. The messy answer, which is often the more memorable one, is that it is the reason the inside of a proton is not remotely as simple as three little particles sitting still and minding their manners. And perhaps that is part of why the gluon makes such a good subject for a slow, reflective evening like this one. It reminds us that the world is often held together by things that do not resemble our first guesses about them. Stability is not always built from calm. Structure is not always built from stillness. Sometimes what keeps a thing together is ceaseless activity, constant exchange, and a rule so strict that nothing involved can ever quite get away from anything else. That is a strange thought, but not an unpleasant one. The universe, at least at this level, is not assembled like flat-packed furniture with a tidy set of parts and a tiny hex key. It is more unruly than that. Matter exists because the underlying ingredients are caught in relationships that do not easily loosen. Gluons are part of that stubbornness. They are the agents of a force so strong and so self-entangled that it creates permanence out of confinement, mass out of interaction, and ordinary solidity out of a world that is anything but quiet. So as we move further in, we're going to need a clearer look at the quarks themselves, at this peculiar idea of colour charge, and at why the strong interaction obeys rules that seem almost designed to offend common sense. Because once you begin to see how gluons carry colour, why they interact with one another, and how that changes everything inside a proton, the whole subject becomes less like a glossary entry and more like a hidden engine room of reality, humming away beneath every atom, every star, and every sleepy thought you have had tonight. If the gluon were named by a committee devoted to realism rather than gentle misdirection, it would almost certainly not be called a gluon. It would be called something far less tidy, something like the impossible binding commotion particle, or the reason protons are not flying apart particle, or perhaps the tiny overachiever that refuses to mind its own business. But physicists, like the rest of humanity, are not always immune to giving very strange things very innocent names. So gluon it is, and with that harmless-sounding little word comes one of the busiest and most consequential actors in the whole visible universe. At first glance, the nickname seems fair enough. Gluons help hold quarks together. Quarks make up protons and neutrons. Protons and neutrons make atomic nuclei. Atomic nuclei sit at the heart of atoms. Atoms make up the familiar material world. Therefore, if you take a deep enough dive beneath your pillow, your bookshelf, your teacup, your walls, your hands, and the entire sleepy architecture of ordinary matter, somewhere down there you find gluons doing essential work. So yes, in a broad sense, they are helping glue reality together. That part is true. The problem is that the word glue suggests something still, passive, and obedient. It suggests a substance you spread onto one surface so another surface will stick to it, after which the glue quietly accepts its role and stops being dramatic. That is precisely where the comparison begins to fail. A gluon does not quietly accept anything. It is not a dab of cosmic paste sitting between quarks like mortar between bricks. It is not even best understood as a tiny object waiting in place for a useful assignment. The gluon belongs to the quantum world, which means that from the start we have to let go of the idea that it behaves like an ordinary thing, with a fixed little path and a modest little personality. In that world, particles are also excitations of fields, and interactions are not neat exchanges between static beads in a box. They are restless, spread out, dynamic processes. The proton is not a miniature fruit bowl containing 3 quarks and a few well-behaved helper particles. It is a highly active region of confined energy, and the gluon is one of the main reasons it stays that way. This is where the subject begins to get more interesting than the schoolbook version. Many people first hear that a proton is made of 3 quarks, and naturally they picture 3 tiny components bound together like passengers strapped into a very small vehicle. It is an understandable image. It is also, unfortunately, the sort of image that starts out useful and then slowly leads your intuition into a ditch. Because a proton is not just 3 quarks in a stable arrangement, and the gluons inside it are not sparse little connectors that step in occasionally, tighten a bolt, and then wait politely for further instruction. The interior of a proton is more like an ongoing event. Things are moving, fluctuating, interacting, and reconfiguring all the time. Quarks exchange gluons. Gluons interact with other gluons. Additional quark and antiquark pairs can briefly appear and vanish. Energy is stored in the field itself. Momentum is shared around in a way that makes the whole object less like a mechanical assembly and more like a tightly confined storm. That is one of the first big lessons of the gluon. Stability in the quantum world does not always come from stillness. Sometimes it comes from constant activity under strict rules. A proton is stable, yes. It can survive for astonishing spans of time, but its stability does not mean it is calm on the inside. In fact, part of what makes it stable is the ceaseless interplay of the strong interaction, with gluons at the centre of it. The gluon is helping create permanence, but it does so through motion, exchange, and a force so intense that the usual everyday images break down almost immediately. You can think of it this way. Imagine describing a city by saying it is held together by roads. There is truth in that. Roads connect to neighbourhoods, allow movement, and make the city function as one unit, rather than a pile of isolated districts. But if you then imagined the roads as quiet strips of pavement, with nothing happening on them, you would miss the life of the city entirely. The important part is not merely that roads exist.
It is that traffic moves across them. People travel, goods circulate, patterns emerge, and the city keeps becoming itself through that motion. The gluon is not a road, of course, but the analogy helps with the emotional shape of the idea. It is not enough to say the gluon holds quarks together. The important thing is that this holding together is an ongoing, active process, one that never really settles into stillness. This makes the gluon very different from the mental picture many people borrow from glue, string, or a tiny hook. The strong interaction is not a rigid tether in the ordinary sense. It is described by a field, and the gluon is the quantum carrier of that field. When quarks interact strongly, they do so through this field and through the gluons associated with it. But unlike the photon, which carries the electromagnetic interaction without itself carrying electric charge, the gluon has a peculiar extra complication. It carries the kind of charge relevant to the strong interaction as well. That means the messenger is also involved in the message. It can interact not only with quarks, but with other gluons too. And once that is true, the whole behavior of the force becomes much richer, much messier, and frankly, much more entertaining. This is one reason the gluon never sits still, even in the most conceptual sense. It does not just pass influence from one quark to another and then leave the scene with a modest nod. It is part of a network of self-interaction.
It contributes to the restless structure of the field itself. It changes the way the force behaves over distance. It changes what it even means to picture the inside of a proton. If you try to imagine it as a neutral postal worker delivering strong force letters door to door, you will be disappointed. The gluon is more like a courier who is also writing the letters, arguing about the contents, rearranging the envelopes, and occasionally becoming part of the furniture. That sounds playful, but it points to a serious physical fact. Much of the familiar matter around us owes its mass not simply to the bare masses of quarks, but to the energy tied up in their interactions. The proton is much heavier than you would expect if you just added together the masses of 3 quarks in the most naive way. A great deal of its mass comes from the energy of confinement and motion inside it, and gluons play a central role in that. So when we say the gluon helps hold everything together, we're not only talking about keeping quarks from wandering off, we're also talking about helping generate the very heft of ordinary matter, the chair beneath you, the bones in your body, the pages of a book, the dust on a windowsill. All of it carries the legacy of these interactions. The gluon is not a decorative accessory in particle physics. It is one of the reasons the visible universe has substance, and yet, for something so important, it is remarkably unwilling to behave in a simple, display-friendly way. You cannot scoop up a gluon and point to it the way you might point to a grain of sand. In experiments, physicists infer its presence through what it does, through the patterns in collisions and the sprays of particles that emerge when protons are smashed together at high energies. The gluon is one of those entities that makes itself known through consequence rather than presentation. It leaves tracks in behavior rather than sitting still for a portrait, which to be fair is very on brand. When people hear that the strong force binds quarks, they often assume that as you move quarks farther apart, the force should weaken in the way many familiar forces do. But the strong interaction has its own peculiar logic. At very short distances, quarks can behave in a surprisingly loose way, as though they are almost free within the cramped space of a proton. Try to separate them over larger distances, however, and the interaction does not politely fade. The system resists. The field stores energy. Pull hard enough, and you do not simply isolate a single quark. Instead, the energy put into separation can create new particles, so that what emerges is not a lonely quark wandering off into the world, but a reshuffling into new bound states. The universe, at least under ordinary conditions, is not interested in offering you a single quark as a souvenir. Gluons are deeply tied to this phenomenon. Their self-interaction is part of what gives the strong force its special character. This is not just a force that acts. It is a force whose own carriers are caught up in the action, and because of that, the field can become concentrated in a way that makes confinement possible. It is as though the very mechanism of communication between quarks also helps close the exits. The result is that quarks remain bound, not because they are sitting in a neatly glued arrangement, but because the underlying field dynamics make isolation extraordinarily difficult. There is something almost comforting about that, oddly enough. We often imagine the deepest layers of reality as clean and elegant in a cold, minimalist way. We picture perfect spheres, exact lines, little silent mechanisms turning in emptiness. But the gluon reminds us that nature is not always built from quiet simplicity. Sometimes it is built from tightly organized commotion. Sometimes the thing that keeps a structure intact is not stillness, but a very disciplined kind of internal chaos. That is a useful correction to our intuition, and not only in physics. A heart is stable because it beats. An atmosphere is stable because it circulates. A living body is stable because countless processes never stop. In their own very different domain, gluons belong to that family of truths. They hold things together by never being fully at rest. The more physicists probed the proton, the clearer this became. High-energy experiments showed that the proton contains not just 3 quarks in any simple sense, but a whole distribution of constituents sharing its momentum. Gluons carry a significant fraction of that momentum. In some regimes, especially at very high energies, they become enormously important. The proton starts to look less like a trio and more like a packed crowd. The old textbook phrase 3 quarks is not false, exactly, but it is incomplete in the same way that saying a city is 3 buildings would be incomplete. Those 3 quarks define certain key properties, yes, but the gluons are everywhere in the structure, shaping the internal dynamics, contributing to the momentum budget, and participating in the restless exchange that makes the proton what it is. This is why the phrase "never sit still" is not just rhetorical decoration. It is close to the physical truth. The gluon is not resting in place inside matter. It is part of a field in motion, part of an ongoing quantum process, part of a constant traffic of interaction. Even the so-called empty space inside a proton is not empty in the everyday sense. It is structured by the field. It is full of possibility and activity. The gluon is woven into that activity so deeply that asking where exactly it is at all times in a classical way becomes the wrong question. A better question is what role it is playing in the field configuration, in the exchange of momentum, in the confinement of quarks, in the generation of mass and structure. The answer, frustratingly and beautifully, is that it is doing all of those things at once. Of course, this can make the gluon sound almost mystical if we are not careful, and it is worth resisting that temptation. There is nothing supernatural going on here. The behavior is strange, yes, but it is not magic. It is the result of a quantum field theory with very specific rules, tested to extraordinary precision. The fact that the rules are not intuitive is not a sign of vagueness. It is a sign that our everyday instincts were formed in a world of apples, shadows, doors, weather, and furniture, not in the interior of hadrons. Reality does not owe our intuition a user-friendly design. Still, one can appreciate the comedy of it. Human beings looked into matter, discovered one of the most unruly ingredients in existence, found that it binds quarks with a force of astonishing complexity, contributes to most of the mass of ordinary matter, interacts with itself, helps prevent isolation of its partners, and generally turns the proton into a crowded quantum storm, and then said, yes, let us call that a gluon. There is a kind of sleepy charm to that decision. It is almost as if the universe knew the topic would need a gentle name to lure us in before the real strangeness began. And the real strangeness does begin here. Because to understand why the gluon behaves this way, we have to look more closely at the special kind of charge involved in the strong interaction. It is not electric charge, it is something else, something with its own rules and its own oddly artistic vocabulary. Quarks carry it, gluons traffic in it, and once that concept comes into focus, the gluon stops looking like a badly behaved blob of force and starts looking like the natural consequence of a much deeper structure, one built around color charge and the peculiar logic of the strong force. To make sense of the gluon, we have to spend a little time with quarks, because gluons do not mean very much in isolation. They are part of a relationship, and like many important relationships, this one becomes harder to understand the moment you try to summarize it too quickly. So let us slow it down and look at the cast of characters properly. Quarks are among the fundamental particles in the standard model of particle physics. They are not made of smaller known pieces. As far as present evidence can tell us, they are basic ingredients. They come in different kinds, usually called flavors, with names that sound as though they were selected by a committee that had either become very tired or very playful. Up, down, charm, strange, top and bottom. For the ordinary matter around us, the main ones are the up and down quarks. Protons and neutrons are built from them. That much is already enough to tell a respectable introductory story. But the moment the strong force enters the room, respectability becomes much harder to maintain. You might think that if quarks are basic particles and the strong force binds them together, then all we need to do is label the particles, label the force, and move on. Unfortunately, the strong force is not interested in being that simple. It comes with its own kind of charge, and this is where the word colour enters the story. Colour charge is the property that determines how quarks take part in the strong interaction. It is not the same thing as electric charge. It does not correspond to visible light. A quark is not literally red, green or blue in any ordinary visual sense. The names are labels, and slightly mischievous ones at that. Still, once the names were chosen, physics had to live with them. So we do indeed talk about quarks carrying red, green or blue colour charge, and antiquarks, to complete the bookkeeping, carry what are called anti-colours. The terminology sounds almost whimsical, but the underlying idea is very serious. The strong force has a three-way structure built into it. Colour charge is how that structure shows up in the language of the theory. This matters because the strong interaction follows rules that are quite different from the ones many people first imagine when they think about forces. With electric charge, there are two basic signs, positive and negative. The interaction between charges can be pictured in a way that is conceptually manageable, even if the full theory is still subtle. With colour charge, the picture becomes more crowded. Instead of one kind of charge with two signs, there is a richer arrangement. Quarks carry colour. Gluons are linked to changes in colour, and the rules that govern how these charges interact produce behaviour that has no close everyday equivalent. One of the easiest ways to begin is with a caution. When you hear the words red, green and blue, do not picture tiny coloured marbles. That mental image has betrayed generations of students. It is understandable, because our brains are built to latch onto sensory analogies. But in this case, the analogy is only a naming scheme. There is no hidden rainbow inside the proton. If you could somehow look into one, which you cannot do in the ordinary visual sense anyway, you would not find a neat little tricolour arrangement glowing like a decorative lamp. What you would find, insofar as the theory and experiments guide us, is a highly active quantum system governed by colour charge and by fields that constantly exchange it. The reason the colour language was appealing is that there are three basic charges involved, and combinations of them can form a kind of neutral state. In visible light, red, green and blue together can combine to produce white. In the theory of the strong interaction, the three colour charges can combine into a colour-neutral arrangement. This is not because the proton is secretly white in a decorative sense. It is because the mathematical structure allows combinations that count as neutral under the strong interaction. A proton, for instance, is built from three quarks, one carrying each of the three colours in a combined state that is colourless overall. A meson, which is a different kind of particle, can be built from a quark and an antiquark whose colour properties cancel into a neutral whole. That idea of colour neutrality is one of the odd but central rules of the strong force. The particles we observe freely in ordinary conditions are not colour-charged objects wandering around on their own. They're colour-neutral combinations. Nature, at least in the low-energy world of familiar matter, seems to insist on this. Quarks stay confined inside colour-neutral groupings. Gluons operate within those systems, but single isolated colour charges do not appear as ordinary free particles in the world around us. That is not an accident. It is a deep feature of the theory. This already makes the strong interaction feel different from electromagnetism. An isolated electric charge can exist. You can have a lone electron. It is perfectly happy, or perhaps not happy, but certainly allowed to move about as an individual particle. A lone quark is another matter entirely. No one has ever observed one in isolation. The reason is not that we simply have not looked carefully enough. The reason is that the strong interaction behaves in a way that makes isolation extraordinarily difficult. That behaviour is tied directly to colour charge, and to the special structure of the field that gluons belong to. Now, let us bring the gluon back into the picture, because this is where things start becoming deliciously inconvenient. A gluon is the carrier of the strong interaction, but it is not a bland neutral courier. It carries colour information itself. That means when a quark emits or absorbs a gluon, its colour charge can change. A quark that was one colour can become another through the exchange. The gluon is associated with that transfer, so the gluon is not simply transmitting an influence while remaining aloof from the charges involved. It is part of the traffic of colour. This is a very big deal. In electromagnetism, the photon does not carry electric charge, so photons do not directly couple to one another in the same rich self-interacting way. But gluons do carry the strong kind of charge, which means they can interact with other gluons. That changes the entire personality of the force. The field can become self-coupled. The carriers of the force are also subject to it. The messenger is caught in its own network. If you are looking for the moment when the strong force stops resembling any tidy household analogy and becomes a category of its own, this is one of the key reasons. It is also one reason the rules of the strong force are so odd from an everyday point of view. When two electric charges interact, the field between them behaves in one broad familiar way. But with colour charge, the self-interaction of gluons changes how the field organises itself. At short distances, quarks behave in a way that can seem surprisingly free. This feature became known as asymptotic freedom, which is a wonderfully formal phrase for something that initially sounds backwards. Inside a proton, where quarks are packed close together, they are not held in place like rigidly glued beads. They move in a way that reflects the weakening of the effective interaction at very short range. Yet if you try to pull them far apart, the situation reverses in a practical sense. The field does not simply fade into irrelevance. Instead, the energy stored in it grows, and the system resists separation. If that sounds rude on the part of the universe, that is because it is rude. You try to extract a quark, and the theory responds by making that plan increasingly expensive. Put in enough energy, and rather than obtaining one lone quark, you create new quark-containing particles. The world rearranges itself so that colour-neutral objects come out instead. It is one of the most striking examples of nature enforcing a rule not by a polite sign on the door, but by redesigning the room while you are still inside it. This property is called confinement, and it is one of the defining outcomes of the strong interaction. Colour-charged particles do not stroll freely through everyday space. They are confined within hadrons, the family of particles that includes protons and neutrons. That single fact does a tremendous amount of work in shaping the visible universe. If quarks could wander around individually the way electrons do, matter would be radically different. Chemistry as we know it would not exist in the same form. Atomic nuclei would not be built from the same stable ingredients. The whole architecture of matter would have to be rewritten. So when we talk about the odd rules of the strong force, we're not just admiring an eccentric bit of theory. We're talking about the very rules that permit the ordinary world to have stable nuclei at all. Quarks come with colour charge. They must combine into colour-neutral states. Gluons transmit changes in colour and also interact among themselves. These features produce confinement. Confinement makes protons and neutrons possible in the form we know them, and from there, atoms, molecules, materials, planets, and sleepy people listening to physics videos can proceed as usual. There is another layer of oddness here that is worth lingering on. The proton is often introduced as being made of 3 quarks, and that is correct in an important bookkeeping sense. Those 3 are the valence quarks, the ones that define the proton's main quantum numbers. But the actual interior of the proton is far more crowded. There are gluons everywhere in the sense relevant to the theory, and there are also transient quark and antiquark pairs appearing from the field and disappearing again. The proton is not merely 3 quarks sitting around waiting for lunch. It is a dynamic system full of exchange and fluctuation. Color charge is constantly being shuffled through gluon interactions. Momentum is being shared. Energy is distributed among many active degrees of freedom. This is another reason the word rules matters so much. The strong interaction is not just a pull between particles. It is a set of constraints and permissions that shape a whole internal economy. Which combinations are allowed? Which states are neutral? How color can change in an exchange? How the field behaves at different scales? How self-interaction among gluons feeds back into the entire system? The result is less like a simple attraction, and more like a highly regulated market in which every transaction alters the structure of the marketplace itself. Now, it is fair to ask why physics ended up with such a strange arrangement in the first place. Why should there be a force with a 3-fold charge, carriers that interact with one another, and a low-energy world in which the charged ingredients are never seen alone? The honest answer is that this is what nature seems to do. The mathematical theory that describes the strong interaction, quantum chromodynamics, was built to match observed features of hadrons and of high-energy scattering experiments, and it has succeeded remarkably well. It is not an arbitrary invention. It is a disciplined framework whose oddness is forced on us by evidence. That said, evidence does not automatically make a picture intuitive. Human intuition is not a universal solvent. It dissolves some problems and leaves others mostly intact. Few of us have daily experience with self-interacting gauge fields and colour confinement. We are excellent at throwing balls, judging distances, locating furniture in a dark room and finding snacks. We are not naturally equipped to imagine why red, green and blue that are not really colours should combine into a colourless proton that contains a sea of gluons which themselves carry colour. That is not a personal failing. That is just a reminder that the universe was under no obligation to make its deepest workings feel familiar. Even so, there are ways to make it less alien. One useful thought is that colour charge is not decoration. It is structure. It is the tag that tells the strong field how to couple to a quark. The quarks do not carry colour because the theory wanted more personality. They carry it because that is the form the interaction takes. And gluons are not unruly because physicists were bored. They are unruly because when the force carriers themselves carry the relevant charge, self-interaction is unavoidable. Once that is built into the theory, many of the strange large-scale consequences follow. This is also where one begins to understand why the gluon is not merely one particle among many. It is part of the architecture of confinement itself. Color charge creates the need for color-neutral combinations. Gluon exchange mediates the dynamics of color. Gluon self-interaction helps shape the field into the peculiar behavior that confines quarks. In that sense, the gluon is not just carrying the force, it is helping define what the force is allowed to become. It is a little humbling, really. The solidity of the world around us depends in part on rules that sound almost absurd when first stated aloud. Matter is built from quarks that carry colours which are not colours. They are bound by gluons that carry colour themselves. Those gluons interact with one another, and because of that, individual quarks cannot normally escape. The result is a world of stable hadrons, atomic nuclei, and everyday matter. Had someone written that into speculative fiction a century ago, an editor might have said it was trying too hard. And yet here it is, not trying hard at all, just quietly being true. Once this framework is in place, the gluon starts to look less like an odd-named particle and more like the natural agent of a very specific set of rules. Quarks carry colour. the strong force acts on colour. The field that carries that force must therefore traffic in colour, but because it traffics in colour, it cannot remain detached from the field it carries. And because it cannot remain detached, it helps create the very wildness that makes the strong interaction so distinct from the others. That whole chain is what turns the gluon from a textbook label into a genuine character in the story. From here, the next step is to get even more precise about what the gluon is beyond the shortcut language, not just the particle that holds quarks together, and not just the messenger of the strong force, but what sort of entity it is in a modern field theory picture, and why the deeper definition matters if we want to understand what it is really doing inside the proton. A textbook will usually tell you that a gluon is the carrier of the strong force, and as first definitions go, that is perfectly respectable. It is short, it is accurate enough to get the door open, and it gives the impression that one has successfully learned something before bed, which is always welcome. But it also leaves out most of the interesting part. In fact, it leaves out so much of the interesting part that it can accidentally make the gluon sound simpler than it really is. It can make it sound like the strong force has its own version of a delivery service, and gluons are the couriers, zipping back and forth between quarks with neat little parcels of interaction. That image is not totally wrong, but it is much too tidy. The real story is stranger, busier, and much more revealing about how modern physics thinks the world is built. So when we ask what a gluon really is, beyond the textbook definition, we are asking for the deeper version. Not the quick classroom slogan, but the more honest account. What kind of thing is it exactly? Is it a tiny object? Is it a wave? Is it a packet of force? Is it a feature of a field? Is it something we can picture directly at all? And why does every attempt to describe it using familiar language end up sounding slightly suspicious, like we are translating from a language with no exact equivalent? The best place to begin is with a fact that applies not just to gluons, but to all particles in the modern quantum field picture. A particle is not best understood as a tiny billiard ball. It can behave in particle-like ways, yes. It can transfer energy and momentum in discrete amounts. It can leave traces in detectors. It can be counted in experiments. But beneath that familiar-sounding word particle is a more fundamental description. Each kind of particle corresponds to a field that exists throughout space, and what we call a particle is a localized quantum excitation of that field. In plainer language, a particle is more like a ripple in something deeper than it is like a hard little grain of matter. This is already a bit of a challenge for intuition, because our ordinary experience trains us to think in terms of objects. Tables, stones, cups, hands, socks that have vanished in the laundry, all objects. We understand them by imagining that they sit somewhere and remain themselves as they move around. Fields are not like that in the everyday sense. A field is something extended through space with values and structure everywhere. The temperature in a room can be thought of as a field. The magnetic influence around a magnet can be thought of as a field. In physics, the fundamental fields are more basic still, and the particles we observe are ways those fields can be excited. So a gluon, at the deepest level we currently use in standard particle physics, is an excitation of the strong interaction field. It is not a blob of glue wedged between quarks. It is not a tiny hook or thread. It is the quantum form taken by the field associated with the strong interaction when that field participates in a discrete exchange. That sentence sounds rather formal, but it is much closer to the truth than the simple cartoon of a proton held together by little sticky pellets. This matters because once you start thinking in terms of fields rather than tiny hidden objects, the gluon begins to make more sense. Not easier, perhaps, but more sense. The strong interaction is not a background property that quarks somehow feel through empty nothingness. It is an active field structure, and quarks couple to that field through color charge. The gluon is what that interaction looks like when it shows up in the quantum language of exchanges and excitations. In a calculation, in a scattering process, in the internal dynamics of a proton, the gluon is the unit of activity associated with the strong field. but even that does not yet tell you what is so unusual about it. To see that, it helps to compare it to a more familiar force carrier, the photon. A photon is the quantum of the electromagnetic field. It carries the electromagnetic interaction. Electrons and other charged particles can emit or absorb photons. In that sense, photons are also force carriers. So far, gluons and photons sound like cousins. Both are associated with fields, both are quanta of interactions, both show up in the mathematical machinery of particle physics as gauge bosons, which is the technical family name for these force-carrying particles. A textbook may happily place them side by side and move on, and yet the family resemblance only goes so far. The photon does not carry electric charge. That means it does not participate in the electromagnetic interaction in the same direct self-entangled way that charged matter does. Gluons are different. A gluon carries the kind of charge relevant to the strong interaction, which means it can interact with other gluons. This single fact changes everything. It means the strong force is not just transmitted by its carriers are also caught inside the very network of interactions they mediate. If you are trying to picture that in a simple mechanical way, it can be frustrating. It is a bit like discovering that the roads in a city are not only pathways for traffic, but are also affected by the traffic in such an immediate way that the roads themselves join the flow, split, merge, and redirect one another. The analogy is not exact, of course, but it captures the feeling of the thing. The gluon is not just a neutral go-between. It is part of the strong interaction in a way that makes the whole system far more active and far less classically tidy. This is why the phrase carrier of the strong force, though useful, is incomplete. It sounds as though the gluon is transporting something separate from itself. In reality, the gluon is the quantum manifestation of the field, whose structure and self-interaction define how the force behaves. It does not merely carry the force the way a waiter carries plates. It is one of the ways the field exists dynamically. It is part of the force at work. There is another complication hiding in the word particle. When people hear that something is a particle, they often imagine that it should be possible to isolate one and examine it in a straightforward way. Pick it out, track it, perhaps even display it with a magnifying glass of truly absurd power. With electrons and photons, at least in broad conceptual terms, that kind of thinking is not entirely hopeless. But with gluons, confinement changes the picture. A free gluon is not something that ordinarily emerges into the world by itself and says hello. The strong interaction prevents color-charged objects from appearing freely under normal conditions, and since gluons themselves are tied to color charge, they do not usually appear as independent, long-lived particles you can simply collect. That leads to a subtle but important point. Gluons are real, in the sense that the theory requires them, and experiments confirm the patterns expected from them. But the way they are real is often indirect. We detect their influence through hadrons, through collision debris, through jets in particle accelerators, through the momentum structure of protons, through the success of quantum chromodynamics in describing strong interaction phenomena. The gluon is not imaginary, but its life in nature is bound up with confinement. It lives inside a theory that does not usually let it stroll onto the stage alone. This can make the whole subject sound slippery. People sometimes hear that a particle is a field excitation, then hear that it cannot usually be isolated, then hear that it may appear as an internal exchange in a calculation, and they begin to suspect that physicists are playing a very elaborate game with words. But there is no trick here. The confusion comes from the fact that ordinary language was not built for quantum field theory. We are trying to use words shaped by chairs and stones and moving cars to describe a domain where what matters most is not object permanence in the everyday sense, but symmetries, fields, allowed interactions, and the quantized structure of those interactions. So what is a gluon really? It is the quantum excitation associated with the gauge field of quantum chromodynamics, the theory of the strong interaction. It is massless in the core theory, which already distinguishes it from some other force carriers. It couples to quarks through colour charge. It also couples to other gluons because it carries colour information itself. It cannot usually be isolated under ordinary conditions because the strong interaction confines colour. And inside hadrons such as protons and neutrons, it is a central part of a dynamic, collective system rather than a decorative extra. That phrase, dynamic, collective system, is worth dwelling on for a moment because it is one of the clearest ways to get beyond the textbook caricature. A proton is not just 3 quarks plus a few gluons for administrative support. It is a bound state arising from a whole interacting field system. The valence quarks matter, certainly. They define important properties of the proton. But the gluons contribute enormously to the internal momentum and energy of the proton, and they are constantly involved in exchanges that shape its structure. In some experimental regimes, the number of relevant gluons becomes very large. The proton begins to look less like 3 stable ingredients, and more like a densely populated quantum environment. This means that asking where the gluon is inside the proton can be the wrong sort of question if it is asked in too classical a way. It is rather like asking where exactly the turbulence is in a storm, as though it were a pebble you could point to. The better question is how the gluon field contributes to the proton structure, how momentum is distributed among quarks and gluons, how the internal state changes with the energy scale at which you probe it, and how the exchange of colour shapes the whole confined system. In other words, the gluon is less a static resident and more part of the living traffic of the proton. There is also a difference between the way we talk about gluons in calculations and the way we talk about what is finally observed. In the mathematical language of particle physics, it is common to describe interactions as being mediated by exchanged gluons. That picture is powerful and useful. But what detectors ultimately observe are not free exchange gluons as tiny labelled pellets. Instead, experiments reveal hadrons and particle jets, patterns in energy flow, and statistical signatures that match the presence and behaviour of gluons. The theory uses gluons as essential internal ingredients, and the observed world confirms that this is the right way to describe the strong interaction, even if the gluon itself is not usually captured as a neat standalone object. The closest many people come to a more public glimpse of gluons is through high-energy collisions. When particles are smashed together in accelerators, quarks and gluons can be violently disturbed, and the aftermath can produce jets of hadrons whose structure reflects the underlying quark and gluon processes. Physicists read these patterns the way a detective might read a chaotic room, not by expecting the culprit to be sitting in a chair waiting to confess, but by inferring what must have happened from the arrangement of the evidence. A gluon in that setting is not a visible marble. It is a necessary part of the event structure, encoded in how the debris organises itself. All of this brings us to a rather important correction to the textbook-style definition. The gluon is not just a mediator between pre-existing objects, it is part of the ontology of the strong interaction itself. It belongs to the fundamental field content of the theory. When quarks exist, the gluon field is not optional background scenery. It is woven into what their interactions are. That is why so much of the proton's mass and momentum can be tied to gluonic activity. The gluon is not a messenger arriving from outside. It is built into the framework of the bound state. And here we begin to see why the gluon is difficult to summarize without sounding either too vague or too technical. If you say it is glue, you mislead people into thinking it is passive. If you say it is a particle, they picture a bead. If you say it is a field excitation, you sound as though you have wandered into a graduate seminar and misplaced the snacks. If you say it is the gauge boson of quantum chromodynamics, you sound accurate but not especially soothing. The truth is that all of these descriptions point in the right direction when handled carefully, but none of them alone is enough. Perhaps the most honest plain language version is this. A gluon is the active quantum unit of the strong field, the thing that makes colour interactions happen, the thing through which quarks exchange colour, the thing whose own ability to carry colour makes the strong interaction radically unlike electromagnetism, and the thing that helps turn hadrons into densely bound, dynamic objects rather than miniature containers of still ingredients. That is a longer definition than any textbook prefers, but the gluon has done very little to earn brevity. There is also a deeper philosophical shift hidden here. In older mechanical intuitions, one tends to imagine that matter is made of little pieces, and forces are secondary influences acting between those pieces. In quantum field theory, that separation becomes less sharp. Particles are excitations of fields, interactions are built into the way fields couple, bound states emerge from the collective behaviour of those fields. The gluon is a good example of why this matters. You cannot really understand it by treating it as an object first and a field effect second. The field picture is primary. The particle language is one way that field behaviour becomes countable and observable. Once you accept that, a lot of the gluon's strange reputation begins to look less like bad behaviour and more like consistency. Of course, it is hard to isolate because the field theory confines colour. Of course, it changes the structure of the force because it carries the relevant charge. Of course, it contributes to the mass and momentum of hadrons because bound states in quantum field theory are energetic collective systems, not just bags of ingredients. The gluon is weird only if one expects the strong interaction to imitate ordinary intuition. If one starts from the logic of the theory, the gluon begins to look inevitable. That does not make it simple, but it does make it clearer. The textbook gives you the label. The fuller picture gives you the role. The gluon is not the strong force in miniature, and it is not a tiny chunk of adhesive. It is the quantized activity of the strong field itself, inseparable from the colour-charged world of quarks and from the complex internal life of hadrons. And once that is on the table, the next question becomes unavoidable because it is one thing to say that gluons carry the strong interaction, but another to explain why they themselves are affected by it so strongly that the whole force takes on its famously unruly character. One of the most unusual things about the gluon is not merely that it carries the strong force, but that it also takes part in that very force itself. This sounds like a small technical detail when stated quickly, but it is really one of the defining features of the strong interaction. It is the reason the gluon cannot behave like a neutral courier. It is the reason the inside of a proton is so busy. It is one of the reasons quarks remain confined, and it is the reason the strong force has a personality so different from the electromagnetic force that everyday intuition begins to wobble almost as soon as the comparison starts. To see why this matters, it helps to begin with the general idea of a force carrier. In modern particle physics, the basic forces are described by fields, and the particles associated with those fields act as the quanta of interaction. That is the formal way of saying that when particles influence one another through a force, there is a field structure behind it, and the exchange of quanta of that field is part of how the interaction is described. In electromagnetism, the relevant quantum is the photon. In the strong interaction, it is the gluon. At first, this makes the two sound similar. Each is a force carrier. Each belongs to the quantum description of a field. Each appears in the theory as part of how particles affect one another. So far, very respectable, very symmetrical, very easy to put into a nice table in a textbook. And then the symmetry starts to crack. The photon carries the electromagnetic interaction, but it does not carry electric charge. That means a photon can be emitted or absorbed by charged particles, yet it is not itself electrically charged in the same direct sense. Because of that, photons do not couple to one another in the rich direct way that charged matter couples to them. They can influence charged particles, but they do not ordinarily gather into a noisy family quarrel with other photons just because they happen to be nearby. The electromagnetic field, in the simple picture most people learn first, behaves in a relatively clean way because the carrier itself remains neutral with respect to the charge it mediates. The gluon does not have that luxury. The gluon carries the relevant kind of charge for the strong interaction, namely colour charge. That means it can interact with quarks, certainly, but it can also interact with other gluons. This one feature changes the entire character of the force. It means the field does not simply extend influence between quarks while remaining detached from the process. The field has an active internal life. Its own quanta are caught inside the same web they help create. The messenger is not outside the conversation. The messenger is arguing too. That is the broad idea. But it deserves a slower walk, because this is where many of the odd rules of the strong force begin to make emotional sense, rather than just appearing as isolated facts on a page. When we say that a quark carries color charge, we mean that it is the kind of particle that the strong interaction acts upon. Color charge is not visual color. It is not red in the way paint is red. It is a label for the kind of charge that the theory of the strong interaction uses. Quarks come with this charge, and because they do, they can emit or absorb gluons. In the process, their color state can change. A quark that was one color can become another when it exchanges a gluon. So the gluon is already more than a passive connector. It is part of the reshuffling of color itself. Now here comes the crucial twist. The gluon is not colorless. It is built from color information in a way that allows it to mediate changes in the color state of quarks. That is why it can do its job. But because it is not neutral with respect to the strong charge, it is also subject to the strong interaction. It does not merely pass the force along, it feels the force too. A gluon can affect another gluon because both belong to the same charged framework of the field. This is the point where many familiar analogies quietly resign. If you imagine a postal service, the letters do not themselves take part in the argument written inside them.
If you imagine couriers, the courier is not normally altered by the political disagreement in the envelope. If you imagine a bridge carrying traffic, the bridge does not usually decide to join the traffic and merge into the lane. Ordinary experience trains us to separate the thing that carries from the thing being carried. The gluon refuses that separation. It carries the strong interaction because it is one of the ways the strong field acts. And because it belongs to that field as a charged quantum, it is entangled with the very dynamics it mediates. This is one of the reasons the strong force becomes so different from the forces people know from ordinary life. A self-interacting force field is not just a channel of influence. It can organize itself in complicated ways. It can concentrate. It can generate collective behavior. It can reshape how the interaction looks at different distances. And that is exactly what happens. At very short distances, quarks can behave as though the strong interaction becomes weaker in an effective sense. This is one of the most surprising and celebrated features of quantum chromodynamics. It is called asymptotic freedom, which sounds faintly like a complicated way of saying that the quarks loosen up when packed close together. Inside a proton, where distances are tiny, quarks are not frozen in place like little stones glued into a sculpture. They move in a way that reflects this weakening of the effective interaction at short range.
But if you try to separate quarks over larger distances, the story changes dramatically. The field between them does not simply fade away in the neat manner one might expect from ordinary force pictures. Instead, the energy associated with the strong field remains substantial, and the system resists the separation. The more you try to pull the quarks apart, the more energy gets stored in the field. Eventually, instead of isolating a single quark, the energy becomes sufficient to create new quark-containing particles, and the system rearranges into new color-neutral combinations. The universe, rather firmly, declines your request for a lonely quark. The self-interaction of gluons is central to this behavior. Because gluons act on one another, the strong field does not spread out in the same way a simpler non-self-interacting field would. Its structure becomes richer, more focused, and more capable of producing confinement. The field lines of the strong interaction do not politely diffuse into insignificance over larger separations in the same, easy fashion people might imagine from a more familiar force. Instead, the self-interacting nature of the field changes how the energy is distributed. That difference lies behind the astonishing fact that quarks are permanently confined inside hadrons under ordinary conditions. So when we say that gluons carry the force and also feel it themselves, we are not pointing out an amusing footnote. We are identifying the engine of the strong force's weirdest behaviour. There is another consequence that often gets less public attention, but is just as important. Because gluons interact with one another, the inside of a proton is not just a few quarks, with occasional gluon exchanges taking place for maintenance. It is a genuinely dynamic environment rich in gluonic activity. Gluons can split into other gluons. They can contribute to the appearance of short-lived quark and antiquark pairs. They can carry substantial portions of the proton's momentum. They are not a side feature. They are part of the proton's inner weather. That is a useful phrase, inner weather. Not because the proton has clouds, though physics would probably find a way if given enough time, but because weather is one of those familiar systems where stability and motion are inseparable. The atmosphere has persistent structure, but it is built from movement, exchange, pressure differences, flow, and constant local change. A proton is stable as a particle, but its stability does not come from internal stillness. It comes from the ongoing structure of a strongly interacting quantum system. Gluons are woven into that motion so deeply that removing them from the picture would remove most of what a proton is. This leads to a remarkable fact about ordinary matter. The masses of the quarks inside a proton account for only a modest part of the proton's total mass in the naive sense. Much of the proton's mass arises from the energy of the strong interaction itself, from confinement, motion, and the activity of the gluon field. In other words, gluons are not just keeping matter together. Through the energy bound up in their interactions, they help give ordinary matter much of its weight. The solid world around you owes a great deal to a force carrier that is far too busy to remain merely a carrier, and this helps correct a common misunderstanding. When people hear that a force particle is massless in the theory, they sometimes imagine it must therefore be insignificant or ghost-like. But massless does not mean unimportant. Photons are massless and light fills the visible world. Gluons are massless in the theory as well, yet through confinement and field energy, they contribute profoundly to the mass of hadrons. The important quantity is not just the bare mass of the carrier itself. It is the role the field plays in the bound state. A crowded, energetic, strongly interacting system can have substantial mass precisely because energy is part of what mass is in modern physics. So the gluon does not need to bring mass into the proton like luggage. It helps create the energetic structure from which the proton's mass emerges. This is where the deeper beauty of the theory starts to show. The strong force is not merely strong because it is large in some vague emotional sense. It is strong because of the structure of the field and the way its charge is organised. The very design of the theory makes the gluon a participant in its own interaction. Once that is true, many of the great features of quantum chromodynamics follow. Self-coupling, confinement, the sea of gluons inside hadrons, the scale dependence of the interaction, the difficulty of isolating quarks, the surprisingly collective origin of hadronic mass. All of these are different branches from the same root. It is also why the gluon refuses simple metaphors. Glue, for example, gives a false impression because glue is usually passive. It sits there, it clings. It may dry in a place you did not intend and mildly ruin your afternoon, but it does not launch into a network of interactions with other packets of glue in order to redefine the nature of the bond itself. The gluon is much more active than that. It is less like glue and more like a charged participant in a crowded negotiation where every message alters the room. The phrase feel, the force themselves, also tells us something about how careful we have to be when describing particles in modern physics. There is a temptation to imagine that particles are first and forces are second. Little pieces of matter exist, and then little packets of influence fly between them. But in quantum field theory, that order is too simplistic. The particles and the fields belong to one framework. The gluon is not a separate messenger added onto a finished set of quarks. It is part of the very field content that defines what strong interaction matter is. A quark without the gluon field is not a physically complete description of a strongly interacting particle. The theory comes as a package. That package is what makes the strong force feel so alive compared with the older mechanical pictures. The field has structure. The carriers have charge. The carriers interact among themselves. Bound states emerge from this entire collective system, rather than from a few simple pairwise attractions. The proton is not built like a small machine assembled from static parts. It is more like a confined pattern of activity that endures because the underlying field theory makes that pattern stable. Once you look at it that way, the gluon stops seeming like a badly behaved exception and starts seeming like a clue. It tells us that matter is not ultimately held together by tiny rigid connectors. It is held together by field dynamics. It tells us that the visible mass of the world is not merely the sum of little ingredients, but the result of energetic relationships. And it tells us that a force can become profoundly different when its own quanta carry the charge they mediate. There is also a certain comedy in the fact that such a concept sits behind such everyday things. Your hands feel solid. A table resists being pushed through the floor. A stone has weight. None of these experiences announces the presence of self-interacting gauge bosons participating in color confinement. And yet the connection is real. Deep beneath ordinary experience, the solidity and mass of matter depend on a network of interactions whose key messenger is incapable of standing outside its own message. This is why the gluon deserves more than a one-line textbook description. It is not simply the particle of the strong force. It is the reason the strong force is the kind of force it is. It carries colour, so it couples to quarks. It carries colour, so it couples to itself. Because it couples to itself, the field becomes highly non-trivial. Because the field becomes highly non-trivial, quarks are confined and hadrons become dense dynamic objects. Because hadrons become dense dynamic objects, much of the mass of ordinary matter emerges from the energy of the interaction itself. All of that is packed into the apparently innocent statement that gluons carry the force and also feel it. And once that has settled in, the next step becomes almost unavoidable. Because if the gluon is already this meddlesome when described carefully, then we can push the point even further. The strong force does not merely have a messenger that is involved in the message. It has a messenger that cannot keep out of its own business at all, and that is where the gluon begins to look less like a neat tool of nature and more like the central troublemaker in the whole microscopic story. By now, the gluon has already lost the right to be described as a polite particle. It is not enough to say that it carries the strong force, because that still sounds far too neat, far too civilized, far too close to the image of a neutral go-between doing a job and then stepping out of the room. The gluon is not a neutral go-between. It is the only messenger in the standard model of everyday matter that becomes deeply entangled in the very business it is supposed to conduct. It does not simply pass influence from quark to quark. It joins the activity, reshapes it, amplifies it, and helps create the entire peculiar personality of the force it mediates. That is what makes it such a fascinating object. If the photon is like a beam of information moving cleanly between charged particles, the gluon is something far more involved. It is the kind of messenger who reads the letter, edits the letter, argues with the sender, rearranges the furniture, and then somehow remains essential to the entire system working at all. The strange part is that this is not a flaw in the theory. It is not an awkward exception. It is exactly what the theory requires, and it is one of the main reasons the strong interaction behaves so differently from anything most of us meet in ordinary life. The basic reason, as we have already begun to see, is that the gluon carries color charge. That one statement sounds modest, but it changes almost everything. A force carrier that does not carry the relevant charge can remain detached from its own field in a limited way. A photon does not have electric charge, so it does not participate in electromagnetism the way an electron does. The photon can move the interaction along without becoming one more charged participant in the process. The gluon cannot do that. Since it carries color charge, it is subject to the strong interaction itself. A gluon can interact with quarks, but it can also interact with other gluons. The strong field is therefore not just a field that affects matter, it is a field with a busy inner life of its own. This is a wonderfully inconvenient fact if your goal is simplicity, and a wonderfully productive fact if your goal is to explain why matter exists in the form it does. Because once the gluon becomes entangled with itself and with other gluons, the strong interaction stops looking like a straightforward attraction and starts becoming a highly structured collective system. The field can bunch in ways a simpler field would not. It can store energy in ways that lead to confinement. It can help turn the interior of a proton into something more like a packed quantum storm than a tidy box of ingredients. And it can make the whole notion of a clean separation between messenger and message collapse almost completely. This is why the phrase "cannot keep out of its own business" is more than a joke.
It is a fairly accurate plain language description of what makes the gluon special. It is not merely involved by accident. It is built to be involved. The theory does not give it a choice. To carry the strong interaction at all, it must carry color. To carry color is to belong to the interaction. And once it belongs to the interaction, it can no longer stand outside it as a neutral courier. You can feel the consequences of this everywhere in the strong force. Start with the proton, that apparently modest resident of the atomic nucleus. The simple school version says a proton contains 3 quarks. That is true in the narrow bookkeeping sense that there are 3 valence quarks whose presence defines certain properties of the proton. But the actual interior is much more crowded. There are gluons constantly being exchanged. There are gluons interacting with one another. There are transient quark and antiquark pairs flickering into relevance and then disappearing again. Momentum is not carried by the 3 valence quarks alone. A significant amount lives in the gluon content of the proton. So the proton is not a neat arrangement of 3 pieces held together by a few support cables. It is a busy bound state produced by a whole interacting field system, and the gluon is one of the main reasons it is busy. If you imagine the proton as a calm little compartment, the gluon ruins that image immediately.
It fills the space, in the sense relevant to the theory, with exchange and activity. It makes the strong field into something dynamic rather than decorative. It helps generate the internal pressure of the system. It participates in the distribution of momentum. It contributes to the energy that becomes the mass of the proton. In other words, the messenger is not standing on the sidelines while matter gets made. The messenger is one of the main builders. There is a deep conceptual shift hiding in that fact. In ordinary thinking, we often imagine objects first and interactions second. First there are things, then there are forces acting between those things. But the gluon pushes us toward a more modern view, where fields and their interactions are part of the basic content of reality from the start. The proton is not 3 pre-existing quarks, plus some optional glue. The proton is an emergent bound state of the full strong interaction system. Quarks matter, certainly, but the gluon field is woven into what the proton is. You cannot peel it away and expect the remainder to make sense as a real particle. That is how far the messenger has inserted itself into its own business. And then there is confinement, perhaps the most famous symptom of this meddling behaviour. Quarks are not seen on their own in ordinary conditions. We do not find a single free quark drifting through space the way we find electrons. This is not because we have simply failed to look carefully enough. It is because the strong interaction behaves in a way that prevents the separation of colour-charged particles into isolated free states. When you try to pull quarks apart, the field between them does not give up in the polite way many forces do. It stores more and more energy. Push hard enough, and the system responds not by releasing a lone quark, but by creating new quark-containing particles, so that colour-neutral combinations emerge instead. The self-involvement of gluons is central to this. Because gluons interact with one another, the strong field does not spread out in the same way as a simpler field. It can become concentrated into structures that make the cost of separation grow rather than gently disappear. The strong interaction therefore acts unlike the familiar long-range force of electricity. It becomes a kind of trap, not because it is malicious, but because its own internal rules make that outcome natural. The gluon is the central troublemaker in those rules. Its refusal to remain neutral is part of what makes confinement possible. That also means the gluon is implicated in one of the most extraordinary facts about ordinary matter. Most of the mass of the proton does not come from simply adding up the small bare masses of the three valence quarks. It comes from the energy of the system, from the motion of quarks, from confinement, and from the activity of the gluon field. So the gluon is not only holding the proton together in some loose verbal sense, it is helping create the very mass of the proton through the energy of interaction. That is quite a thing for a so-called messenger to be doing. It would be like saying the postal service does not merely deliver the city, but also builds most of its buildings while in transit. This is one reason I keep coming back to the word activity. The gluon is not best imagined as a static presence. Even saying it sits inside the proton is not really the right emotional picture. It is part of an active field configuration, part of a traffic of exchange, part of a ceaseless reshaping of colour and momentum. The proton is stable, yes, but that stability is not built from stillness. It is built from tightly organised motion and interaction. The gluon helps maintain the pattern precisely by never becoming a passive component. The phrase "cannot keep out of its own business" also captures something slightly funny about the elegance of physics. Theories often look clean when written in compact form. There are beautiful symmetries, neat structures, and concise principles. But when those principles are allowed to unfold into physical consequences, they can create a world far messier and more animated than the compact mathematics first suggests. The gluon is a good example. The theory says the strong interaction is based on a certain kind of gauge symmetry. Quarks carry colour. The gauge field must therefore have the corresponding structure. From that structure it follows that the gluons carry colour too. And from that follows the whole chain of self-interaction, confinement, gluon-rich hadrons, and mass emerging from energetic field dynamics. A compact idea, then a riot of consequences. This is also what makes the strong force so distinct from the electromagnetic one. Electromagnetism allows us to think in terms that are comparatively gentle. Charges interact through a field whose carrier stays neutral with respect to the charge it mediates. Light can travel freely through space over enormous distances. Electric forces weaken with distance in a familiar way. The theory is deep, but the intuition is manageable. The strong force, by contrast, has carriers that are themselves charged under the interaction. That makes the field non-linear in its behaviour. It folds back into itself. It changes character with scale. It confines its own sources. It produces bound states whose mass is dominated by interaction energy. One begins to see why the gluon does not deserve to be described as a quiet little particle. There is another side to this that becomes especially important in high-energy physics. As you probe protons at higher and higher energies, the gluon content becomes more and more significant. The proton reveals itself not as a fixed three-quark object, but as a system rich in gluons and C-quarks. The closer you look, in a sense, the less the proton resembles a simple trio and the more it resembles a dense crowd. That crowd is not random. It follows the rules of quantum chromodynamics. But it does mean that the gluon is central not only in holding the proton together, but in determining what the proton looks like when examined in detail. The messenger has moved so far into the story that it has become one of the main characters. Now, a careful listener may wonder whether all this talk of gluons interacting with themselves risks making them sound like tiny living creatures with opinions, which would admittedly improve some undergraduate lectures but would be bad physics. So it is worth saying clearly that self-interaction does not mean personality, in any literal sense. It means the quantum field associated with gluons has terms in the theory that allow gluons to couple directly to one another. It is a structural fact about the field, not a mood. But the reason the informal language is so tempting is that the consequences really do look, from the outside, as though the gluon refuses to remain detached. It keeps feeding back into the very process it is supposed to mediate. And that feedback is everything. It is why the strong interaction changes with distance the way it does. It is why quarks can appear almost free at very short range and yet remain confined at larger scales. It is why hadrons are such deeply collective objects. It is why the mass of visible matter comes out the way it does. It is why the proton is more like a weather system than a bead necklace. The gluon is not merely one ingredient among others. It is one of the reasons the whole recipe behaves as it does. There is a lovely irony in all this. The visible world feels solid, dependable, and mostly calm. A table sits where it should. A stone has weight. Your hand rests on a blanket and encounters resistance rather than dissolving into nonsense. Yet beneath that ordinary reliability lies a theory whose central binding particle is anything but calm. The gluon helps produce the stability of matter by participating in a deeply unstable seeming sea of exchange and field energy. The ordinary world is built on disciplined microscopic restlessness. This is not unique to the strong force, perhaps. Many stable systems depend on ongoing activity. A heartbeat is stable because it continues. An ecosystem is stable because countless interactions persist. A flame has shape because fuel and heat keep flowing in a certain pattern. The proton belongs to that family of truths. It endures not because nothing is happening, but because the right things keep happening inside it. The gluon is one of the chief keepers of that ongoing process. So the only messenger that cannot keep out of its own business turns out to be exactly the messenger the universe needed for the strong interaction. A detached carrier would have given us a different kind of force. A neutral intermediary would not have produced the same confinement, the same gluon-rich interiors of hadrons, the same emergence of mass from interaction energy. The gluon is troublesome in exactly the productive way nature seems to favour. It complicates the theory, deepens the structure, and in doing so makes ordinary matter possible. And that leaves us with a slightly more focused version of the big mystery. We now know that the gluon is not passive, not neutral, and not easy to isolate. We know that its self-involvement shapes the behaviour of the strong force. But there is an even more striking consequence waiting just ahead, because all of this meddling leads directly to one of the hardest and most important facts about the strong interaction, the reason no one ever meets a gluon alone. There is a very simple way to tell that the gluon does not behave like an ordinary little particle. No one ever meets one on its own. No one opens a detector and finds a single lonely gluon sitting there like a cat that has wandered into the wrong garden. No one bottles one. No one watches one drift freely through space in the way light travels across a room or electrons move through a wire. Gluons are absolutely central to the structure of matter, and yet they do not show up as tidy, independent guests in the ordinary world. They live inside hadrons, inside the strong interaction, inside the internal activity of protons and neutrons and other particles built from quarks. They are real, essential, and stubbornly unwilling to appear alone. This is not a temporary inconvenience. It is not merely that the experiments are difficult, though they certainly are. It is not that physicists have somehow not looked hard enough. It is that the theory of the strong interaction itself seems to forbid the kind of easy isolation we might expect from more familiar particles. That deep feature is called confinement, and it is one of the defining facts of quantum chromodynamics. It is also one of the reasons the gluon has such an unusual reputation. It is a force carrier that helps shape the visible universe, but it belongs to a force so peculiar that neither its sources nor its own quanta normally appear by themselves in nature. To understand confinement, it helps to begin with the opposite expectation. the one most of us bring from everyday life and from the first things we learn about forces. If two objects are bound together by a force, then one naturally imagines that pulling them apart should eventually weaken that force. Stretch a spring too far and it may break. Pull two magnets apart and their influence fades with distance. Separate electric charges and the effect becomes weaker in the ordinary way. We are used to the thought that distance loosens things. In the familiar world, that is a very reasonable habit of mind. The strong interaction does not reward that habit. When quarks are very close together, as they are inside a proton or neutron, the strong interaction behaves in a way that can make them seem relatively loose, almost as though they have some freedom of movement within their tiny confined region. This is already an odd result, but it has been confirmed over and over in both theory and experiment. Yet when you try to separate quarks farther apart, the interaction does not simply fade into harmlessness. Instead, the field between them stores more and more energy. The system resists. The farther you try to pull the quarks apart, the more costly the separation becomes. That is not how most people expect a force to behave. It feels at first almost rude. The universe appears to say that short-range motion is one thing, but actual escape is another matter entirely. The quarks can jostle about inside their prison, but they are not allowed a proper exit. And the gluon is right at the centre of this arrangement, because the strong field that produces confinement is the field whose quantum excitations are gluons. The gluon does not merely witness confinement, it helps create it. One of the better ways to begin picturing this without misleading ourselves too much is to stop imagining the strong interaction as a loose cloud spreading in all directions between quarks. In electromagnetism, the field from a charge spreads outward in a way that gives the force its familiar weakening with distance. The strong interaction is different because the field is shaped by the self-interaction of gluons. The gluons carry colour charge themselves, so the field does not remain a passive background. It can organise itself into something more concentrated, more focused. Instead of dispersing in the same easy way, the energy of the strong field tends to remain trapped in a narrower region between colour charges. People often describe this with the image of a string or tube under tension. The image is not exact, but it gives the right emotional feel. As two quarks are pulled apart, the field energy between them grows rather than simply thinning away. The system begins to resemble something being stretched, something storing more and more energy as the separation increases. That growing energy is the reason you do not simply obtain a free quark by pulling hard enough. The moment you put enough energy into the attempt, the system finds another solution. Instead of releasing an isolated colour-charged particle, it creates new quark containing states. What comes out are new hadrons, new colour-neutral combinations, not lonely quarks and not lonely gluons. This is one of the strangest and most beautiful bits of logic in all of particle physics. Try to force the strong interaction to give you an isolated constituent, and the energy you invest does not pay you back with freedom. It pays you back with more matter. The field stores what you give it, and once the amount becomes large enough, new particle pairs can appear so that colour-neutral structures remain the final result. It is as if the theory would rather make extra furniture than let you carry a single screw out of the house. That helps explain why no one ever meets a gluon alone. A gluon carries colour information. That means it is part of the colour-charged world governed by confinement. A free gluon would itself be a colour object moving independently through space, and the theory resists that just as it resists a free quark. Under ordinary conditions, gluons remain bound into colour-neutral systems. They contribute to hadrons. They shape jets in high-energy collisions. They leave unmistakable signatures in scattering experiments. But they do not stroll into the open as single, long-lived free particles ready for polite inspection. This can feel slightly unfair to the human imagination. We are used to learning about things by isolating them. Find one, hold it still, see what it does, then build the bigger picture from there. That method has worked very well across much of science. You can isolate a drop of water, a grain of salt, a bacterium, a photon in certain controlled settings, an electron in a trap. The gluon frustrates that instinct because the very act of trying to isolate it invokes the field structure that prevents the isolation. In a sense, the closer you get to the gluon by force, the more the strong interaction responds by refusing the terms of your approach. This is why confinement is not merely an experimental limitation. It is a structural statement about nature. The strong interaction seems to prefer colour-neutral objects in the world we ordinarily observe. Protons, neutrons, mesons, and other hadrons are colourless as complete states. Their constituents are not colourless by themselves, but the total combination is. That is the kind of object the theory permits to emerge into everyday existence. A single quark is not such an object. A single gluon is not such an object. The door to freedom is locked by the rules of colour. There is a lovely irony here, because the gluon was named to suggest sticking things together, and yet what it really participates in is not simple sticking. It participates in a kind of permanent social contract for quarks, one from which no individual is normally excused. The strong interaction does not say merely stay nearby. It says remain part of a colour-neutral whole. The gluon is one of the ways that rule is enforced, and because the gluon itself belongs to the same charged world, it cannot escape the arrangement either. This has huge consequences for how we know gluons exist at all. Since we do not normally observe free gluons directly, we learn about them through their effects. High-energy collisions are a particularly important example. Smash particles together hard enough, and the underlying quark and gluon structure becomes visible indirectly through the sprays of hadrons that emerge. These sprays, called jets, are not single quarks or single gluons escaping into the world. They are the aftermath of energetic partons, meaning quarks or gluons, being produced and then turning into many colour-neutral hadrons as confinement takes over again. In the detector, what you see is not a little label reading gluon. What you see is a pattern of debris whose structure tells you a gluon was part of the event. That is very much in keeping with the gluon's personality. It does not introduce itself. It leaves evidence. It disturbs the room and relies on you to reconstruct what happened. Confinement also explains why the strong interaction is not just another force in the same style as electromagnetism. If you had only learned the phrase force carrier, you might imagine a set of parallel stories. The photon carries one force, the gluon carries another, and perhaps the differences are just matters of strength or range. But confinement means the strong interaction is qualitatively different. It hides its own charged ingredients. It builds the visible world out of colourless composites. It makes the interior of hadrons rich and active, while refusing to display the constituents one by one as free particles. The theory is not just stronger, it is more secretive. That secrecy is not absolute, of course. Physics has become remarkably good at interrogating the strong interaction without ever forcing it to give up its deepest rule. Particle accelerators, scattering experiments, and detailed theoretical calculations allow physicists to infer the distribution of quarks and gluons inside protons with tremendous sophistication. We can study how momentum is shared. We can detect signatures of gluon-initiated jets. We can investigate how the internal structure changes with the energy scale of the probe. In all of this, confinement is not an obstacle that makes knowledge impossible. It is a condition that shapes the form knowledge must take. We do not learn the strong interaction by strolling through a field of free quarks and free gluons with butterfly nets. We learn it through traces, patterns, distributions, and the stubborn consistency of the theory. There is also a deeper reason confinement matters for the existence of the ordinary world. If quarks and gluons were freely roaming particles under everyday conditions, matter would not have the same stable architecture. Nuclei would not be built from bound protons and neutrons in the same way. Chemistry would not unfold atop the same foundations. The fact that the strong interaction confines its ingredients into hadrons is part of what allows atomic nuclei to exist as recognizable building blocks. So the same rule that frustrates our wish to isolate a gluon is also one of the rules that make the visible universe manageable at human scales. It is another reminder that stability often comes from restrictions. We tend to think freedom is what allows structure, but in physics that is often not the case. Structure emerges from constraints. Atoms exist because electrons occupy allowed states. Solids have properties because particles obey exclusion rules in electromagnetic arrangements. And hadrons exist because quarks and gluons are confined into color-neutral holes. The gluon is part of that discipline. Its refusal to appear alone is not a failure of nature to be cooperative. It is part of the system's success in making matter stable. There is, however, an important subtlety worth keeping in view. When we say no one ever meets a gluon alone, we mean under ordinary conditions and in the form of asymptotically free particles, the kind of independent objects that can emerge from an interaction and travel far away as themselves. In extreme environments such as the unimaginably hot conditions of the early universe or the tiny fireballs created in heavy ion collisions, the behavior of quarks and gluons can change. Under those circumstances, matter may enter a different state, often called a quark-gluon plasma, where the usual hadronic boundaries are no longer the right description. Even there, though, the story is not one of neatly catching a single relaxed gluon and asking how its day has been. The physics becomes collective in a different way, not simpler. That point is worth making because confinement is sometimes described too casually, as though it were just a matter of particles being tied together like dogs on leashes. It is more profound than that. It is a property of the theory that shapes which states can exist freely and which cannot. It tells you what kind of particles nature is willing to present as independent in the low-energy world. Quarks and gluons are fundamental ingredients in the theory, but hadrons are the freestanding objects nature usually gives us. This also means the proton is not merely a hiding place. It is the proper habitat of the gluon under ordinary conditions. A proton is not a sealed box with a few hidden items inside. It is a bound state, an active, confined system in which quarks and gluons make sense as constituents, precisely because confinement keeps them from turning into independent public objects. To ask why no one ever meets a gluon alone is therefore also to ask what a proton really is, and the answer is not three particles plus accessories. It is a color-neutral bundle of strong interaction activity, with gluons everywhere in the internal story. There is something quietly satisfying about that. The gluon is one of the most important particles in the visible universe, and yet it never seeks the spotlight in a direct way. It works through relationships, through shared states, through collective structure. It is known by consequence rather than by solitary display. That may sound almost noble, though I suspect the gluon would object to any attempt at moral characterization, and instead continue behaving according to the strict mathematics of quantum chromodynamics. Still, from a human point of view, it does change the tone of the subject. The gluon is not a particle you meet in isolation and then fit into a larger model. It is a particle you infer from the internal life of matter. You learn it by studying bound states, energetic collisions, and the stubborn rule that colour remains confined. You come to know it as part of a crowd, and once that settles in, the next step is almost unavoidable, because if no one ever meets a gluon alone, then the only honest place to look for it is where it actually lives, inside the proton itself, not as a neat set of three quarks in a tidy little arrangement, but as a dense and restless storm of gluons shaping the whole interior from moment to moment. Once confinement is on the table, the proton starts to look very different from the simple image many of us first learned. In the beginner version, a proton is made of three quarks. That statement is useful. It is not false. It tells you something important about the proton, and without it the subject would be much harder to enter. But it is also the kind of statement that becomes less complete the longer you stare at it. The proton is not a neat little container with three tiny residents sitting inside like sensible tenants who pay their rent on time and stay mostly out of trouble. It is not a box with three quarks arranged in a stable pattern, while a few gluons hover nearby to keep the peace. The real proton is much busier than that. It is a bound state full of exchange, field energy, fluctuating quark pairs, and above all an enormous amount of gluonic activity. In a very real sense, the proton is a storm of gluons as much as it is a collection of quarks. That can sound like an exaggeration the first time you hear it, especially if the image of 3 quarks has had years to settle in your mind. After all, schoolbooks, diagrams, and public science explanations often lean heavily on the 3-quark picture. There is a good reason for that. The proton does have 3 valence quarks, specifically 2 up quarks and 1 down quark, and those valence quarks determine important features such as the proton's electric charge and other key quantum properties. If you ask what makes a proton rather than some other hadron, the valence quarks are absolutely part of the answer. So the simplified picture earns its place. The difficulty is that it can quietly suggest a level of emptiness and calm inside the proton that simply is not there. The moment physicists began probing the proton in more detail, especially through high-energy scattering experiments, it became clear that the proton is not mostly empty space with 3 little objects in it, nor is it a rigid structure. What experiments revealed is that the proton contains many active constituents sharing its momentum, and the gluons are not minor extras in that story. They carry a very substantial fraction of the proton's momentum. In some regimes, especially when you probe the proton at higher and higher energies, the number of relevant gluons grows dramatically. The proton begins to look less like a trio and more like a crowd. This is one of those shifts in physics that seems small in wording and huge in meaning. The textbook proton is 3 quarks. The real proton, as described by quantum chromodynamics and explored in scattering experiments, is a dynamic system in which the valence quarks live inside a sea of gluons and short-lived quark and antiquark pairs. These additional quarks are not the ones that define the proton in the same basic bookkeeping way as the valence quarks do, but they are still part of its physical structure. They appear because the gluon field is active. Gluons can produce quark and antiquark pairs. Gluons can split into more gluons. Energy and momentum are constantly being redistributed through the field. So the proton is not merely built from quarks and held together by gluons. It is built from the whole active interplay of quarks and gluons together. That is why the phrase storm of gluons is not just a decorative metaphor. It points to something real about the internal life of the proton. When you probe a proton, you're not peeking into a tiny box with 3 hard particles rattling around. You are interrogating a bound state of a strongly interacting quantum field. Inside that bound state, the gluon field is not a background feature. It is one of the main actors. It carries momentum. It shapes the internal pressure of the proton. It contributes to the energy that becomes the proton's mass. It drives fluctuations that produce additional quark content. It links the whole system together through the constant exchange of colour. This also means that the word inside has to be handled with care. In ordinary language, inside suggests a container with clear walls and objects placed within it. A proton does not have an inside in that simple classical sense. It is not like a walnut with a shell and a few hidden structures. It is a confined quantum state. The constituents do not sit in fixed positions in the ordinary way. Their behaviour is described by distributions, fields, probabilities, and dynamic interactions that depend on the scale at which you probe them. Asking where exactly a gluon is inside the proton at every moment is rather like asking where exactly the traffic jam is inside a city, while the streets and vehicles themselves are changing in response to one another. The question has some meaning, but only if you ask it in the right formal language. The simpler picture of a few objects parked in a compartment will not survive the attempt. A good way to appreciate this is to think about how the proton appears in different kinds of questions. If you ask a very broad question, such as what basic quark content defines the proton, then the answer with 2 up quarks and 1 down quark is exactly the right level of description. But if you ask how the proton's momentum is distributed among its constituents in a high-energy collision, or what its internal structure looks like to a very energetic probe, then the answer changes. The proton reveals a rich population of gluons and C quarks. The closer and harder you look, the less the old picture of three tidy components feels adequate. There is a certain irony in this, because the proton is one of the most familiar particles in nature. Every atom in every ordinary object contains them in its nucleus, except the simplest hydrogen nucleus, which is just one proton by itself. So one might expect that something so common would have a fairly simple interior. But common things in nature often turn out not to be simple at all. A drop of water looks ordinary until you start talking about hydrogen bonding and statistical mechanics. Air looks empty until you describe fluid dynamics. A cell looks simple until you start naming its machinery and soon regret having started. The proton belongs to that family of familiar things with an unexpectedly crowded internal life. And the gluon is central to that crowding. Because gluons carry the strong interaction and also feel it themselves, they do not behave like a sparse set of connectors. They multiply, they interact, they shape the field environment inside the proton. At high energies, they can become so numerous in the relevant description that the proton starts to look like a gluon-dominated object. This does not mean the valence quarks vanish or become unimportant. It means that the physical reality of the proton includes much more than those three quarks alone. This is especially important if one wants to understand where the proton gets its mass. If you simply add up the bare masses of the valence quarks, you do not come close to the full mass of the proton. Most of that mass comes from the energy of the strong interaction itself, from confinement, from the motion of the constituents, and from the activity of the gluon field. So when you hold something in your hand and notice that it has weight, you're not mainly experiencing the simple sum of tiny constituent masses. You're experiencing in part the energy of gluons and quarks locked into a confined, highly active state. The mass of ordinary matter is deeply tied to the storm inside the proton. That fact alone should probably make the gluon much more famous than it is. It is hard to think of a more important invisible contribution than helping generate most of the mass of the visible world. And yet the gluon remains one of those particles that most people only encounter if they wander far enough into particle physics to get slightly lost. Perhaps that is fitting. The gluon seems to prefer influence over publicity. There is another reason the three-quark image can be misleading. It suggests that the proton is made from fixed ingredients in fixed amounts, like a recipe card. But the real proton is a quantum object, and quantum objects are not built from still ingredients arranged once and for all. They are states with fluctuating content. In the proton, the valence quarks are persistent in the sense that they define the proton's identity, but the surrounding sea of gluons and quark pairs is constantly active. A gluon may split into a quark and antiquark pair. Gluons may split into more gluons. Those processes do not mean the proton ceases to be a proton. They are part of what the proton is. This is why physicists often talk in terms of partons when discussing high-energy probes of the proton. The word parton is a more flexible label for the constituents that matter in a given scattering process, including quarks, antiquarks, and gluons. It reflects the fact that what you see inside the proton depends on the scale and energy of the probe. At one level, 3 valence quarks are the important story. At another, a dense swarm of partons becomes the relevant picture. The proton is not pretending to be inconsistent here. It is simply a quantum system that reveals different aspects of itself, depending on how you ask the question. That point is worth dwelling on because it helps rescue the beginner picture without letting it dominate too much. The 3 quark story is not wrong. It is a low-resolution summary of one important layer of truth. The problem begins when the summary is mistaken for the whole structure. It is like saying the Earth is land and water. True, certainly, useful for a child with a globe, but not enough if your next task is to understand climate, ocean circulation, plate tectonics, and the movement of carbon through ecosystems. At that stage, the simplified description starts to look less like a foundation and more like a polite oversimplification. The proton is similar. 3 quarks is the globe on the shelf. The gluon storm is the weather, the oceans, the crust, the atmosphere, and the whole moving system. It also changes the emotional shape of the proton. In the old classroom picture, the proton feels almost mechanical, a small assembly of fixed bits. In the fuller picture, it feels alive in the strictly physical sense of being full of ongoing processes. Not alive in the biological sense, of course. The proton is not secretly harbouring ambitions, but it is active, collective, and sustained by continuing field dynamics. Its identity persists through that activity rather than in spite of it. Again, this is one of those places where quantum field theory asks us to let go of the old idea that stability must mean stillness. If you probe deeper into the mathematics, the gluon content of the proton becomes even more striking. At small momentum fractions, the number of gluons relevant to the description rises rapidly. The proton appears increasingly dense with gluonic degrees of freedom. This is one of the reasons modern experiments and future colliders are so interested in mapping gluon distributions with greater precision. The proton is not merely a solved object. It is a rich system still teaching us how strongly interacting matter organizes itself, and much of that lesson is written in gluons. This is also why the proton is a wonderful example of how modern physics replaces the language of things with the language of fields and states. A proton is not a tiny bead. It is not a bag. It is not a shell around miniature contents. It is a localized, stable bound state arising from the dynamics of quantum chromodynamics. That sentence is more accurate, but admittedly less friendly to bedtime listening, so one often returns to softer images: weather system, storm, crowd, busy interior. These images are imperfect, but they gesture in the right direction. They remind us that what matters inside the proton is not a static arrangement, but an ongoing pattern. And once you accept that, the gluon becomes easier to place in the story. It is not a supporting actor that holds the cast together from the margins. It is part of the cast, part of the script, and part of the stage machinery all at once. The gluon helps bind the valence quarks, yes, but it also fills the proton with field energy and dynamical complexity. It is involved in the sea of short-lived quark pairs. It carries momentum. It contributes to the proton's mass. It helps determine what the proton looks like to high-energy probes. There is no honest version of the proton that leaves the gluon as a footnote. It is perhaps worth saying aloud just how strange this is from an everyday point of view. The proton is one of the basic building blocks of ordinary matter, and yet its most faithful modern description is not that of a hard particle, with smaller hard parts inside it. Instead, it is a strongly interacting quantum state, in which gluons play such a central role that the phrase made of 3 quarks becomes a rough sketch rather than a full portrait. If someone invented this in fiction, it might sound like the kind of thing written to impress rather than to clarify. But nature seems quite comfortable with arrangements that are stranger than our first descriptions. There is something else hidden in the storm image that matters. A storm is not just busy, it also has structure. It has pressure patterns, flows, zones of greater and lesser intensity, behaviour that depends on scale, and dynamics that cannot be reduced to a few static objects. That is part of why the metaphor works better than the image of a box. The proton is not random inside. The gluon activity follows the rules of quantum chromodynamics. The distributions can be measured, the patterns can be modelled, the whole system is lawful, even if it is not simple. So the proton is not chaotic in the sense of being shapeless, it is richly organised motion. This matters when one thinks about the future of particle physics as well. Understanding the proton more deeply is not a side quest. It is essential for interpreting collider experiments, for making precise predictions, and for testing the standard model in regimes where new phenomena might hide. If the proton were just a box of 3 quarks, many calculations would be far easier, but the proton insists on being itself, which means insisting on its gluon-rich structure. The reward for respecting that complexity is that we learn not only about the proton, but about how strong interaction matter works in general. So when people say the proton contains 3 quarks, it is best to hear an invisible extra sentence attached to the end. 3 valence quarks, yes, and also a great deal more. a sea of gluons, a sea of transient quark pairs, a shifting distribution of momentum and energy, a confined state whose mass is largely interaction energy, a quantum object whose internal life depends on the self-interacting field of the strong force. Leave out that extra sentence, and the picture becomes too still. Put it back in, and the proton begins to look like the remarkable thing it really is. And from there, another idea starts to come into focus almost by itself. If the proton is so full of gluonic activity, if its apparent interior is really a dense state of field and exchange rather than a little cavity with contents, then the notion of empty space at this scale begins to break down as well, because the gluon field is not just inside particles as a decorative ingredient, it is part of the deeper structure beneath what we usually call emptiness. That idea takes us somewhere even stranger than the inside of the proton, because once you accept that the proton is not a tidy container of three quarks, but a dense, active state of quarks and gluons, a more unsettling question begins to press itself forward. What exactly are those quarks and gluons living in? What is the background? What is the stage? What do we really mean when we say there is space between things? In ordinary life, empty space feels like the easiest thing in the world to understand. It is what is left when the furniture is removed. It is the air in a room after you carry out the boxes. It is the stretch between two objects. It is the gap on a shelf, the quiet part of the sky. The space between your hand and the table before you touch it. Empty space in everyday thought is just nothing much. It is an absence, a place where matter is not. And for most practical purposes, that ordinary idea works perfectly well. You can set down a glass because there is empty space on the table. You can walk through a doorway because there is empty space where the wall is not. In daily life, the concept behaves itself. Then physics arrives and quietly ruins the simplicity of it. In modern field theory, empty space is not really empty in the old sense. It is not a blank stage waiting passively for particles to wander across it. It is the ground state of a set of fields, and those fields do not vanish merely because no obvious particles are present. They remain there as the underlying structure of the world. The electromagnetic field does not disappear from reality just because a room looks visually still. The electron field does not blink out when there are no free electrons passing through your lamp, and the gluon field, which belongs to the strong interaction, is also part of that deeper fabric. It is not something invented only inside protons like a local repair tool. It is a field of nature, part of the very framework beneath the visible world. This is one of the biggest mental shifts the subject asks of us. The world is not made of objects sitting in empty nothingness. It is made of fields, and what we call objects are often stable patterns or excitations in those fields. Once you begin thinking that way, empty space stops being simple absence and starts looking more like a condition, a lowest energy arrangement, a quiet state of a very active underlying system. Quiet does not mean non-existent. It only means not excited in the most obvious way. That matters enormously for the gluon, because if you picture the gluon only as a little particle darting around inside protons, you miss the deeper picture. The gluon belongs to a field that extends through reality. That field is not merely switched on when quarks are nearby, and switched off everywhere else like a very punctual hallway light. It is part of the world at all times. The reason we notice it most dramatically inside hadrons is that those are the places where colour-charged quarks and gluons form confined bound states. But the field itself is more fundamental than any one hadron. It is part of the architecture beneath them. At first, this can sound too large, almost too grand, because we are not used to thinking of something so exotic as part of the ordinary space itself. Light feels easier because we see it. Electricity feels easier because our technology constantly reminds us of it. The strong interaction feels hidden because it is confined to the atomic nucleus and to the interior of hadrons. It does not announce itself with sparks or bright beams in everyday life. And yet that hidden quality should not mislead us into thinking it is less basic. The gluon field is one of the great background structures of the visible universe. It is one of the reasons particles have the properties they do, one of the reasons hadrons exist at all, and one of the reasons empty space at very small scales is not a blank nothing, but a physically meaningful state. This becomes clearer when we remember that the proton itself is a localized, stable excitation of fields, not a miniature box. The quarks are excitations of quark fields. The gluons are excitations of the gluon field. The proton is what happens when those fields organize into a confined, color-neutral bound state. If that is what a proton is, then the apparent emptiness around it cannot be thought of as some absolute void into which it is dropped like a pebble into a bucket. The surrounding space is already the domain of the same underlying fields. The proton is a structured state of them, not an object separate from them in the old mechanical sense. That is a subtle point, but it changes everything about how reality is pictured. In the older imagination, matter and space are fundamentally separate categories. Matter is the stuff. Space is the emptiness around the stuff. In the field picture, that separation softens. Space is not merely a neutral emptiness. It is where the fields are. Matter is one of the organized ways those fields can behave. The gluon field is therefore not floating in space as a foreign resident. It is part of what gives modern physics its very notion of a physical vacuum. The word vacuum, by the way, is one of those nice examples of scientific vocabulary that sounds simpler than it is. In ordinary language, a vacuum means a place with nothing in it, or close enough to nothing for household purposes. In modern physics, a vacuum means the lowest energy state of the fields. That may be a state with no particles present in the everyday counting sense, but it is not the same as absolute nothingness. Fields remain, structure remains, possibilities remain. The vacuum is a physical state, not the disappearance of physics. For the strong interaction, this is especially important because the vacuum is not featureless. The gluon field does not merely wait around doing absolutely nothing until a proton happens to pass through. The strong interaction vacuum has structure. It has a non-trivial character. It is one of the reasons the strong force behaves as it does, and one of the reasons the world of hadrons has the properties it has. This is where the subject can become intimidating in technical treatments, because one starts hearing about vacuum structure, condensates, symmetry breaking, and all sorts of phrases that sound as though someone misplaced a blackboard. But the core idea can be stated more gently. The ground state of the strong interaction is not bland. It is not the physical equivalent of an empty room with all the lights off. It has built-in richness. A good way to feel the difference is to consider what would happen if empty space really were just nothing. If it were truly nothing in the most absolute sense, then fields would have no persistent background state. There would be no meaningful vacuum properties, no restless underlying framework. But modern physics does not work that way. The fields define what kinds of particles can exist, how they interact, and what sorts of stable states can emerge. The vacuum is the calmest condition of that framework, but it still belongs to the framework. The gluon field does not vanish from reality between protons like a guest who leaves whenever conversation slows down. It remains part of the world. This can sound faintly mystical if one is not careful, so it is worth keeping it concrete. The gluon field beneath reality does not mean that space is secretly filled with little hidden globs of gluon goo. It does not mean the room around you is a soup of free gluons bouncing off the curtains. Confinement still rules. Free gluons do not ordinarily roam about as isolated particles. What it means is that the field associated with the strong interaction is a basic ingredient of nature, and the vacuum state of that field is not equivalent to a blank nothing. The world is built on the presence of such fields whether or not we are currently observing dramatic excitations of them. That helps explain a number of things that otherwise feel disconnected. It helps explain why the proton is so different from the simple sum of three quark masses. It helps explain why hadrons emerge as collective bound states with substantial mass generated by interaction energy. It helps explain why the strong interaction has a deep structural role in the visible universe, even though its carriers do not appear as free household particles. Beneath the apparent simplicity of ordinary matter lies a vacuum and a field content that are already highly non-trivial. There is also something profoundly practical about this once you step back from the intimidating language. The reason the world has stable protons and neutrons is not merely that quarks happen to like one another. It is that the strong field and its vacuum structure permits certain bound states and enforce confinement. That is not an extra feature tacked on after the fact. It is part of the ground rules. So the solidity of the visible universe depends not just on particles, but on what the vacuum of the underlying fields is like. Empty space is one of the conditions that makes matter possible, not merely a blank gap left over when matter is absent. That is a strange sentence to say out loud, but it is one of the most important ideas in modern physics. Empty space is not just where matter is not. It is part of why matter can be what it is. The gluon field plays a particularly important role here, because it is tied to confinement and to the emergence of hadron structure. The proton is not dropped into a neutral void. It is a stable state in a world where the strong field already has its own vacuum character. This is one reason the strong interaction is so hard to reduce to simple pairwise forces between little particles. The background itself matters, the field itself matters, the vacuum itself matters. You cannot really understand the proton by pretending it lives in nothing. It lives in a world already defined by quantum chromodynamics. This is also where the familiar phrase beneath reality begins to earn its keep. Not beneath in the sense of physically underneath your feet, of course, as though there were a lower basement below the carpet where gluons are conducting private meetings. Beneath in the sense of underlying, prior in description, more basic than the visible arrangements we encounter first. The gluon field is part of the underlying physical story from which protons, neutrons, and much of ordinary matter emerge. The visible world sits on top of that deeper framework in the conceptual sense, not because it floats over it like a raft, but because it is built from it. You can see this in the way particle physics talks about what is fundamental. The old instinct is to ask what things are made of, then what those things are made of, and so on, as though the deepest truth must always be a smaller and smaller object. The field picture changes that habit. The deepest level is not necessarily the tiniest bead. It is often the field and the rules governing its behaviour. The gluon field is more basic than any one gluon, in the same way the ocean is more basic than any one wave. The wave is how the field announces itself locally and dynamically. The field is the enduring structure beneath that event. Of course, like all analogies, the ocean one eventually becomes too friendly and should not be trusted too far. The gluon field is not made of water. It is not a material medium in the old 19th century sense. It is a quantum field. But the analogy helps with one point. A calm sea is not no sea. Likewise, a vacuum state is not no field. It is the quietest condition of the field, not the absence of it. And once that thought settles in, the phrase empty space begins to feel a little less empty. The room around you is still ordinary. Your ceiling is still your ceiling. Your blanket is still your blanket. Nothing about the immediate human world becomes unusable just because quantum fields are underneath the description. Yet there is a quiet change in perspective. The apparent calm of the world no longer looks like simple absence between objects. It looks like a low-energy arrangement of deeper structures, one in which certain particles can exist, certain bound states can form, and certain kinds of matter can remain stable over cosmic time. The gluon field is part of that calm. Hidden, yes. Usually confined to its most dramatic visible consequences inside hadrons, yes. But no less real for that. It is one of the reasons the proton is possible. One of the reasons the neutron is possible. One of the reasons atomic nuclei exist in a world where chemistry can happen. Beneath every table, every star, every grain of dust, every sleepy thought about particle physics, there is not a blank nothing but a set of quantum fields whose quiet states are already doing important work. This also helps explain why modern physics can feel both more abstract and more concrete than older pictures at the same time. More abstract, because instead of imagining hard particles in empty space, we must talk about fields, vacua, and bound states. More concrete, because those fields explain real measurable properties of matter with extraordinary success. The proton mass is not a philosophical decoration, it is a physical number. Confinement is not a metaphor, it is a property reflected in experiments. The vacuum structure of the strong interaction is not a poetic flourish. It is part of the best theory we have for how the visible world holds together at the hadronic level. Perhaps the most unsettling but useful lesson here is that nothing in physics is rarely nothing. An empty region may contain no atoms, no dust, no air worth mentioning, and still not qualify as sheer absence. The fields remain. Their ground states remain. Their capacity for excitation remains. Their influence on what kinds of stable matter are possible remains. The world is quieter than it looks in some ways, but not emptier. And the gluon belongs fully to that quiet depth. It is not merely the unruly particle inside the proton, it is the local quantum face of a deeper field that helps define what the strong interaction is everywhere. Most of the time, that field does not show itself to us as a free gluon flying across the room. Confinement sees to that. But its presence is written into the very possibility of hadronic matter, into the vacuum beneath the visible scene, into the hidden groundwork of the ordinary world. So by the time we say that empty space is not empty, we're no longer making a dramatic slogan for its own sake. We are saying something very specific. We are saying that the apparent emptiness around matter is actually the lowest energy state of a world of fields. We are saying that the gluon field is one of those fields. We are saying that the strong interaction is built into reality more deeply than any image of little particles floating in blank nothingness could ever suggest. And once that becomes clear, the next step almost takes itself. Because if the gluon field is already part of the deeper fabric of the world, then the most extreme places to see its behaviour are not only inside protons, but in the hottest, earliest moments of the universe, and in the violent collisions where matter briefly forgets how to remain ordinary. If the proton shows us what gluons are doing under ordinary conditions, then extreme energies show us what happens when the usual boundaries begin to loosen. This is where the gluon stops looking like a hidden supporting character inside matter, and starts looking like one of the main architects of a much more violent world. In a proton at rest, or at least at ordinary low energies by particle physics standards, the gluon is already busy enough. It binds quarks, interacts with other gluons, helps generate mass, and fills the proton with a dense internal life that is nothing like a simple box of 3 particles. But raise the energy high enough, and the whole story becomes more crowded, more collective, and more revealing. Gluons multiply in importance. The proton starts to look increasingly gluon-rich. Collisions become less like impacts between compact objects, and more like encounters between dense dynamic fields. And if we turn the clock far enough back, to the first tiny fraction of a second after the universe began expanding, matter itself enters a regime where the familiar hadrons had not yet settled into their ordinary forms. In that setting, gluons are not hidden at all. They are part of the main event. This is one of the reasons high-energy physics can feel so dramatic, even when the underlying ideas are quite disciplined. It is not only that accelerators are large and expensive, and built with enough engineering seriousness to make ordinary machinery look shy, it is that when particles are pushed to extreme energies, they allow the strong interaction to reveal parts of its character that are much harder to see in the calm low-energy world. The proton, which in a schoolbook looks so modest, becomes a complicated and rather crowded target. Its gluon content matters enormously. The outcomes of collisions depend on that gluon content, and in heavy ion experiments, where entire atomic nuclei are smashed together at immense energies, the resulting fireball can briefly enter a state where the ordinary hadronic packaging of quarks and gluons is no longer the right description. Before getting to that, it helps to understand why energy changes the gluon story so much. One of the most important lessons of modern particle physics is that a particle is not the same object under every scale of questioning. The way a proton appears depends on how hard you probe it. At lower resolution, the 3 valence quarks are a useful summary. At higher resolution, the interior becomes busier, and more of the proton's quark and gluon structure comes into view. At very high energies, gluons become especially prominent. In a practical sense, the proton starts to look like a place where gluons are everywhere in the description that matters. This does not mean the valence quarks stop existing. It means that the active population of gluons becomes increasingly central to the behavior of the proton in a collision. There is something almost mischievous about this. The more energy you use to examine matter, the less matter resembles the quiet little collection of basic ingredients you thought you were examining. It becomes more like a crowd at a railway station after some unexpected announcement, with particles and fields all responding to one another in ways that make any neat diagram look optimistic. Gluons, because they can interact with themselves, are especially good at making the crowd larger and more unruly. At high energies, they can proliferate in the relevant description. The proton becomes rich in low-momentum gluons. The internal picture grows denser. And because these gluons are central to how collisions unfold, understanding them becomes one of the major jobs of modern collider physics. This is not a minor technical matter. When protons collide at enormous energies, such as in the great particle accelerators of the modern era, what actually interact are the proton's constituents. Quarks can scatter, gluons can scatter. Quarks and gluons together can produce new particles. The proton is not a single indivisible cannonball smashing into another identical cannonball. It is a composite object, and its gluon structure is deeply important in determining what happens. In many cases, gluon-initiated processes dominate. So if you want to predict what a collider should see, or search for rare events hiding in the debris, you need to know a great deal about the gluon distributions inside the proton. The gluon is not just some hidden curiosity of theory. It is a practical and central part of the experimental story. And yet even here the gluon refuses to become simple. You do not see a free gluon entering the detector and introducing itself. Confinement still ensures that what emerges at the end are hadrons, jets, and patterns of energy flow. But inside the theoretical description of the collision, and in the interpretation of the final state, gluons are everywhere. They help generate particle sprays. They contribute to the formation of jets whose properties differ in statistically meaningful ways from quark-initiated jets. They shape the event rates of many important processes. They influence how momentum is distributed before the collision, and how energy is released after it. In a sense, collider physics is full of gluons without ever displaying one as a solitary little object. That already tells us something interesting about the phrase gluon chaos. It is not chaos in the sloppy sense of lawlessness. The equations of quantum chromodynamics are still in charge. The calculations are hard, certainly. The events in a detector can look messy enough to make a neat human heart feel slightly overwhelmed. But the mess follows rules. It is structured complexity. It is what happens when a self-interacting field becomes the dominant actor in a high-energy environment. So the word chaos here really means an overwhelming abundance of strongly interacting activity, not the breakdown of physical law. One of the most striking consequences of this comes when not just individual protons, but whole heavy nuclei are collided at tremendous energies. In those experiments, the goal is not only to study the internal structure of a proton, but to push nuclear matter into a regime where the ordinary hadronic picture breaks down for a brief moment. Under normal conditions, quarks and gluons are confined inside protons, neutrons, and other hadrons. But if you create a region of sufficiently high temperature and energy density, the matter can enter a state in which those hadronic boundaries are no longer the most useful description. Instead, one gets a quark-gluon plasma, a short-lived state of strongly interacting matter in which quarks and gluons move in a more collective medium. This phrase, quark-gluon plasma, can sound a little misleading if taken too casually. it does not mean a neat gas of isolated free quarks and free gluons politely mingling in a container. It is not a dilute soup where each particle has finally escaped its old obligations and is now enjoying some personal freedom. In fact, one of the surprising lessons from heavy ion collisions has been that this plasma behaves less like a weakly interacting gas and more like a strongly coupled fluid. It flows, it has collective motion, it responds as a medium. Once again, the strong interaction declines to become simple even under extreme conditions. It merely becomes collective in a new way. There is something deeply satisfying about that. If one had only heard the phrase deconfined matter, one might imagine that the strong force would finally relax into something almost easy. Instead, when nuclei are collided hard enough to produce this new state, the resulting matter still displays the signs of a rich interacting system. Gluons are central to that story. The earliest moments of the fireball are dominated by gluonic fields and dense, strong interaction dynamics. The matter then expands, cools, and eventually hadronizes, meaning it turns back into ordinary hadrons that detectors can observe. What experiments record are the remnants, the after effects, the final particles emerging after the brief hot collective state has lived and vanished. From those traces, physicists reconstruct the properties of the medium that existed for only the tiniest fraction of a second. This is one of the most extraordinary things human beings have ever learned to do. We create conditions, on a microscopic scale, and for almost no time at all, that resemble aspects of the early universe, then infer the properties of that short-lived state from the debris. It is difficult not to be impressed by that, even at bedtime, and the early universe is really where the story reaches its natural wider setting, long before atoms formed, long before nuclei settled into familiar matter, long before stars and planets and the possibility of sleepy physics videos. The universe was hotter and denser beyond ordinary imagination. In those earliest moments, matter was not arranged into stable protons and neutrons the way it is now. The temperature was too high, the energy density too intense. The cosmos was in a state where quarks and gluons belonged to a hot, dense medium rather than to the quiet interiors of individual hadrons. As the universe expanded and cooled, it passed through transitions in which the strong interaction took on the confined hadronic form that would later allow nuclei and atoms to exist. That means the present calm world is not just built on the strong interaction in the abstract. It is the cooled and organized descendant of a much more extreme gluon-rich phase. The early universe was not born with protons already neatly assembled and waiting for chemistry lessons. It had to cool into that condition. Before that happened, the quark and gluon content of matter belonged to a hotter collective state. Gluons were not hidden residents inside hadrons because hadrons, in the familiar sense, had not yet become the relevant stable units. The universe had not yet settled into the low-energy order we now take for granted. This helps reveal something profound about the gluon. In ordinary matter it seems hidden. In the proton it is active but confined. In a collider it appears through energetic processes and complex debris. In the earliest universe it belonged to the dominant thermal medium out of which hadronic matter later emerged. So the gluon is not merely an obscure particle tied to a niche corner of nuclear physics. It is one of the key actors in the history of matter itself. It helped shape the transition from a hot primordial state to the structured world of protons, neutrons, nuclei, and eventually atoms. If one wanted a particle with both microscopic mischief and cosmic significance, the gluon is an excellent candidate. There is also a lovely continuity between the small and the large here. The same theory that explains why no one ever sees a free quark in the quiet conditions of modern matter also guides our understanding of the hottest fireballs in the laboratory and the earlier stages of the cosmos. Quantum chromodynamics is not a local patchwork explanation for one special type of experiment. It is the framework connecting the proton on your page of notes, the jets in a collider detector, the plasma in heavy ion collisions, and the thermal history of the early universe. Across all these scales, the gluon remains central, sometimes hidden in hadrons, sometimes dominating the internal structure of high-energy protons, sometimes part of a hot collective fluid, always refusing to be reduced to the harmless image suggested by its name. The Collider story adds another useful lesson as well. At extreme energies, one can no longer get away with simple pictures that ignore the collective role of gluons. The proton's gluon density becomes crucial. Event predictions depend on it. Searches for new particles depend on understanding it. The interpretation of what counts as ordinary background and what might count as something genuinely novel depends on it. So even in the very practical business of testing the standard model and looking for physics beyond it, the gluon is one of the main reasons life becomes complicated. The proton brings its gluon storm with it into every collision, and every precise prediction has to reckon with that fact. And then there is the almost philosophical lesson. Extreme energies do not merely break things apart. They reveal how much structure was hidden in what seemed calm. In ordinary life, a proton looks like a stable little building block. In a high-energy collision, that calm object reveals a teeming internal society. In the quiet world around us, matter feels permanent and settled. In the early universe, it belonged to a hotter, more collective stage of existence. The gluon sits right at the heart of this shift from appearance to deeper description. It is one of the reasons the world looks simple from far away and gloriously unreasonable up close. Of course, it is worth being careful with the drama. The early universe was not chaotic in the sense of being random nonsense. Nor are collider events merely violent for the sake of spectacle. What makes them important is that they follow the theory so faithfully that they allow us to test it under conditions radically different from ordinary matter. The quark-gluon plasma is not just some hot blur. It has measurable properties. Its flow can be studied. Its transport behaviour can be inferred. The gluon-rich initial state of a collision can be modelled and compared with data. All of this is science in the most disciplined sense. Yet the emotional effect remains striking. The calm, visible world emerges from a theory whose extreme behaviour is dense, collective, and intensely active. That should perhaps make the ordinary proton feel more dramatic in hindsight. The storm inside it is not a domestic little curiosity. It is a remnant and a local expression of a force whose full behaviour includes the hottest known matter ever created in laboratories and the earliest strongly interacting phase of the universe itself. The gluon carries that history with it, not because a single gluon remembers the early universe in any conscious or literal sense, but because the same field and the same underlying rules govern both the tiny bound state in a proton and the fireball of the primordial cosmos. A quiet object on your desk and a hot plasma in a collider are farther apart in feeling than in theory, and perhaps that is one of the most appealing things about this subject. It reminds us that the ordinary and the extreme are often made from the same ingredients under different conditions. The proton in a hydrogen nucleus and the plasma of the early universe are not unrelated worlds. They are different regimes of the same underlying reality. Gluons help connect them. Hidden in one case, collective in another, but always essential. So when we speak of gluon chaos at extreme energies, we are really speaking about what happens when the full personality of the strong interaction comes closer to the surface. The gluon-rich structure of the proton becomes impossible to ignore. Heavy ion collisions briefly create matter where hadronic boundaries give way to a collective quark-gluon medium. The early universe itself once passed through such conditions before cooling into the confined matter we know. All of that follows from a force carrier that not only carries the interaction but also belongs to it so deeply that it can never remain detached. Which brings us very naturally to the final question that has been gathering in the background all along, because after following the gluon from the proton to the vacuum, from confinement to collider fireballs, the pattern is unmistakable. It never behaves in the calm, neutral way one first expects. It binds, but through restlessness. It hides, but leaves enormous consequences. It mediates a force, but is trapped in that force itself. And that raises the bigger point still waiting to be said plainly. Not just what the gluon does, but what its refusal to behave actually reveals about the way nature is built. By this point, the gluon has accumulated a rather long list of offences against ordinary intuition. It carries a force, but is also caught inside that force. It helps bind quarks, but does so through constant activity rather than calm attachment. It contributes to the stability of matter, yet it never behaves like a quiet, stabilizing presence. It cannot usually be isolated. It fills the proton with restless internal structure. It helps generate most of the mass of ordinary matter without itself being the sort of thing you would ever meet in a simple, standalone way. If you are looking for a particle that behaves neatly, predictably, and in accordance with the first picture most people would form, the gluon would not make the shortlist. So the obvious question is why? Why does the gluon refuse to behave in the tidy way the name seems to promise? Why is it not just a little binding particle passing politely between quarks and leaving them in peace? Why does it insist on self-interaction, confinement, field energy, and all the other features that turn the strong force into such a singular part of modern physics? The deepest answer is not that the gluon is especially rebellious by personality, though that is a pleasant way to talk about it late at night. The deeper answer is that the gluon is behaving exactly as the structure of nature requires. What looks like misbehaviour from the perspective of everyday intuition is actually consistency at the level of the theory. The gluon refuses to behave only because our first expectations were built for the wrong kind of world. That is an important thing to notice, because so much of science involves this very pattern. A phenomenon first appears unreasonable, awkward, or almost deliberately difficult. Then, once the right framework is found, the unreasonable thing becomes inevitable. The Earth moving around the Sun once felt like a challenge to common sense. Time running differently under motion and gravity once sounded absurd. Light behaving as both wave and particle has never exactly become cosy, and yet it fits into a larger framework that makes it unavoidable. The gluon belongs to that family of truths. It does not fit the old picture because the old picture was never going to be enough. At the heart of the matter is this: nature, at least in the domain of the strong interaction, is not built from tiny solid parts connected by little passive bonds. It is built from fields, charges, symmetries, and the allowed ways those things can interact. The gluon is the quantum expression of the strong field. Quarks carry colour charge. The strong field must therefore couple to colour, and because of the particular structure of that coupling, the gluon itself carries colour information too. Once that is true, everything else begins to follow. The force carrier interacts with its own kind. The field becomes self-coupled. The interaction changes its character with scale. Quarks become confined. Hadrons become collective objects. Mass emerges from the energy of the confined system. The visible world acquires a solidity that is not the simple sum of little hidden ingredients. Seen from that perspective, the gluon is not misbehaving at all. It is telling the truth about what matter really is, and that truth is not especially intuitive. We grow up in a medium-sized world of chairs, rain, doors, tools, clocks, and food containers that never open the right way on the first attempt. In that world, stable things usually seem to be stable because they are at rest, or because their parts are fastened together in a straightforward way. A brick wall stands because bricks sit still. A shelf holds because wood and screws stay where they are. We naturally import that mechanical picture downward into the microscopic world. We imagine that atoms must be tiny stable assemblies, nuclei must be smaller stable assemblies, and perhaps eventually one reaches a final set of little pieces arranged in miniature stillness. The gluon tells us that this is not how the deepest structure works. A proton is stable, yes, but not because it is quiet on the inside. It is stable because the strong interaction produces a persistent pattern of activity. Quarks move. Gluons are exchanged. Gluons interact with gluons. Quark and antiquark pairs appear and vanish. Energy is stored in the field. The whole object persists not despite that motion, but through it. Stability is not the absence of activity. Stability is the endurance of an organised process. That is a remarkably important lesson, and not only for particle physics. It is one of the broader themes that nature returns to again and again. Many stable systems are not static. A heartbeat is stable because it continues. An ecosystem is stable because countless interactions keep happening. A star is stable because pressure and gravity remain in balance through ceaseless internal processes. The proton belongs to that same style of reality. The gluon reveals that the world is often held together by disciplined motion rather than by stillness. There is another lesson tucked inside this, one that may be even more unsettling. The gluon shows that what we call an object is often less fundamental than the interactions that sustain it. In everyday language, we treat things as primary and relations as secondary. First there is the object, then there is what the object does to other objects. In the world of quantum fields, that order begins to reverse. The proton is not first a little thing and then later a site of interactions. It is a bound state created by interactions from the start. Its identity is inseparable from the strong field that shapes it. The gluon is therefore not a secondary accessory added to matter after matter already exists. It is part of what matter is, at least for the strongly interacting particles that make up atomic nuclei. This can feel like a philosophical claim, but it is not just philosophy. It has direct physical consequences. It explains why the proton mass is much larger than the bare masses of its valence quarks alone. It explains why the proton looks gluon-rich when probed at high energy. It explains why quarks cannot be isolated under ordinary conditions. It explains why ordinary matter has the stable hadronic building blocks that it does. The gluon's strange behaviour is not an ornament on the theory. It is one of the main engines of the visible world. It also reveals something almost mischievous about the difference between names and reality. To call this particle a gluon is to smuggle in an image of passivity. Glue sticks. Glue holds. Glue is annoying when misplaced, but it does not usually reinvent the entire logic of the objects it joins. The gluon is far more unruly than that. It is not a passive binder. It is an active participant in a self-interacting field. And yet the innocent name is useful in its own way because it allows us to feel the gap between our first guess and the truth. The word says one thing, the physics says much more, and in that gap one can almost watch intuition being re-educated. The gluon also reveals that emptiness is not what it seems. If the strong interaction were merely a force between little particles in an otherwise blank void, its behaviour would already be strange enough. But the deeper picture is richer still. The gluon belongs to a field that is part of the underlying structure of reality. The vacuum is not simple nothingness. The proton is not a little object dropped into blank space. It is a stable state of fields in a world where those fields already define the physical stage. So the gluon helps teach another uncomfortable but necessary lesson. Nature is not built from things in emptiness. It is built from fields whose quietest states are already physically meaningful. This changes the emotional shape of reality quite a bit. The ordinary world feels solid because our senses report stable objects, surfaces and distances. Nothing about daily life demands that we think in terms of quantum fields and non-trivial vacua. Yet underneath that calm human scale, the world is not quiet in the old mechanical sense. Matter is structured field activity. Empty space is not sheer absence. Mass is often emergent energy. Stability is organised motion. The gluon, for all its obscurity, is one of the clearest guides to that larger way of seeing. There is a further lesson too, and this one has to do with humility. Human beings are very good at assuming that the most intuitive picture is probably close to the truth. It is an understandable mistake. Intuition is useful. It keeps us from walking into walls and putting kettles in strange places. But intuition is local. It evolved for surviving at human scales. It was never meant to explain the inside of a proton. The gluon is one of those cases where nature asks us to give up the hope that deep reality will resemble comfortable common sense. In return, it offers something better than comfort. It offers consistency. The picture is strange, but it holds together. and there is something deeply satisfying about that. Once you accept the rules, the gluon's behaviour stops looking arbitrary. Of course, it interacts with itself because it carries the relevant charge. Of course, the strong force behaves differently from electromagnetism because its carriers are not neutral with respect to the field. Of course, quarks are confined because the field stores energy in the way it does. Of course, protons are not just three little masses added together because the bound state includes huge amounts of interaction energy. What first looked like a collection of unrelated oddities turns out to be one coherent pattern. The gluon is not a pile of exceptions. It is a clue to the whole design. That design tells us something else as well. The visible world is, in a sense, made from hidden trouble. The calmness of ordinary matter depends on a microscopic regime that is anything but calm. The proton seems simple from a distance because the strong interaction has organized a great deal of internal activity into a stable form. This is a recurring theme in nature. The smoothness we experience often rests on layers of hidden complexity. A fluid seems continuous because we do not see the molecules. A solid seems rigid because we do not feel the electromagnetic negotiations between atoms. A proton seems like a tiny object because we do not perceive the storm of gluons inside it. The gluon teaches us that ordinary appearance is often the surface of deeper, busier rules. It also reminds us that the deepest reality is not always the most visible. Photons are easy to celebrate because they are tied to light. Electrons are easy to celebrate because electricity and chemistry advertise them so effectively. Gluons hide behind hadrons, confinement and indirect detection. They do not show themselves freely. They are known by inference, by collider signatures, by the internal momentum of protons, by the success of quantum chromodynamics. And yet despite that hiddenness, they are central to the mass and structure of the world around us. That too is revealing. Nature does not rank importance by visibility. By now, perhaps the most remarkable thing about the gluon is not that it is strange, but that its strangeness is so productive. Because it interacts with itself, the strong interaction develops its unique character. Because of that character, quarks are confined. Because quarks are confined, hadrons exist as stable building blocks. Because hadrons exist, atomic nuclei can form. Because atomic nuclei form, atoms and chemistry and stars and planets and living organisms become possible. It is a long chain, but it is not fantasy. The ordinary world depends on a force carrier that refuses to remain detached from its own force. That may be the biggest point of all. Nature does not always build the world from simple pieces connected in simple ways. Sometimes it builds the world from rules that are self-involved, layered and relational. Sometimes the thing that carries the interaction is changed by the interaction. Sometimes the source of order is not passivity but persistent exchange. Sometimes what looks like bad behaviour at one level turns out to be the exact reason the larger world works. And that, I think, is what the gluon really reveals. It reveals that reality is deeper than object-based intuition. It reveals that matter is more like a sustained pattern than a pile of miniature stones. It reveals that mass can emerge from energy and confinement, rather than merely from tiny pre-packed weights. It reveals that the vacuum is not blank. It reveals that hidden fields and hidden symmetry shape everything familiar, without ever asking for public recognition. Most of all, it reveals that the universe is comfortable with forms of organisation that look complicated from the outside and turn out to be astonishingly coherent once you understand the rules. There is a quiet comfort in that, even though the subject itself is so unruly. The gluon does not make the universe feel less intelligible. In an odd way, it makes it feel more intelligible because it shows that even the strangest behaviour is not random. It belongs to a structure. It fits. The strong force is difficult, yes. The proton is busy, yes. Empty space is not empty, yes. But all of these are parts of one consistent story. The gluon is difficult because nature is precise, not because nature is careless. So if someone asked, very simply, what a gluon really is and why it refuses to behave, the final answer would be something like this. A gluon is the quantum of the strong field, the carrier of the interaction that binds quarks into hadrons. It refuses to behave like an ordinary messenger because it carries the very charge it mediates, which makes it interact with itself and turns the strong force into a deeply collective, confining, mass-generating part of reality. And what that reveals about nature is that the world is built less from quiet little objects than from active fields, stable patterns, and hidden rules whose consequences reach all the way up to the ordinary solidity of matter. That is quite a lot to ask of one strangely named particle. And yet the gluon seems to manage it. So the next time the world feels solid and uncomplicated, it may be worth remembering that underneath every table, every wall, every book, every hand, and every drifting late-night thought, there is no tiny static scaffold holding things together in silence. There is a deeper story than that, one full of quarks, fields, confinement, and gluons busily refusing to behave, which is perhaps the very reason the universe manages to hold together at all. And wherever you happen to be listening from tonight, whether the room is quiet or the rain is ticking softly outside or the day has simply been longer than expected, I hope this small tour through the strong force has given your mind something interesting to settle into. Because there is something oddly reassuring in knowing that even the most stubborn parts of nature are not stubborn for nothing. They are stubborn in service of a structure, and from that structure come protons, atoms, stars, planets, and the ordinary world resting around you now.